Hi, Ashutosh. Hello.
Hello, ma'am. Good
Yeah, yeah,
afternoon. How are you, ma'am?
yeah, I'm good. I'm good. How are you?
I'm doing good, ma'am. I'm just trying to change that background shared by Nikhil.
Yeah. Same with me also.
Sure, ma'am.
So you can go to change start video and you can do the virtual background change from there. It will get changed.
Where is that, Nikhil?
And on the left bottom side, you will see
Uh,
start video, mute and start video. So in start video, there is a
okay.
drop down arrows there.
Yeah, sure. Got
Then
it, got it.
then select choose virtual background, and then you can
See,
change.
got it. Nikhil, is it okay?
Yes, ma'am.
Yes, ma'am.
Fine.
Just screen coming, right?
But आप नहीं दिख रहा मैम. You are not visible.
Why is that so? Okay, fine.
Now I can see.
Got it.
Good evening, Ashutosh sir. This is Meghna Sharma.
Good evening, Meghna.
Yeah, I completed my PhD under Nilima ma'am in
Yeah,
2021.
ma'am. Great. I heard about you that you are, inspired fellow at IIT Jodhpur, right?
Yes, I'll join soon somewhere. Like I am applying in multiple IITs right now. So I'm
Mhm.
trying to get into the system right now. Yes, sir.
Ashutosh, our patent got granted 2 days back.
Yes,
Sorry,
sir.
ma'am.
Meghna has
Ma'am.
developed a setup, test setup. So that got
Mhm.
granted 2 days before.
My goodness, that's great. Many congratulations to Dr. Meghna and you as well. That's great, ma'am.
Thank you so much, sir. Thank
Great.
you.
And she is here in the
Great.
campus now. She came from
Yeah,
Bombay.
yes, sir.
That's nice.
I'll meet you.
Oh.
I'll meet you, sir.
Yeah. Please. Great leadership, great followers, great students.
Hopefully.
Seriously, it's great. It feels nice to see students like, you are amazing. Nice.
Thank you, sir.
Where is Professor Reddy? Didn't he join it?
Yeah, he's
Hey.
there in the guest house, so he'll be joining. I met him.
Perfect.
Hi, Malaya. Good evening, everyone.
Good evening.
How are
Hi.
you?
I'm fine.
I can see you. I just was going through. I just saw your name. So nice that you joined.
Yeah. Actually, just now I have come from college,
Oh, okay,
So-
okay. Meghna, somebody's asking for the link in the group. Can you please check it out?
Sure, I'm sure.
Coordinate. இது வீடியோ தெரியாம இது பண்ணிக்கலாம்.
Hi, Dr. Jaipriya.
Madam, good afternoon, ma'am.
Good afternoon. How are you?
Ma'am, good afternoon.
Good afternoon. Good afternoon.
Fine, ma'am.
Good afternoon, ma'am.
Hi, good afternoon. So I think we have Professor Reddy also joined. Sir, good afternoon. Hi, Ankit.
Yeah, good evening, ma'am. Yeah.
Good evening.
Yeah.
Ankit, my colleague Dr. Ashutosh is there. Professor Reddy is there.
Okay, yeah.
Ashutosh, Dr. Ankit Karge is a very good friend and a collaborator of mine.
Mhm.
Hello, Dr. Ankit. How are you? Dr. Ashutosh this side.
I'm good, I'm good. How's everything? Yeah. And
I'm
good
good,
evening, Professor Reddy. I think it's Reddy
Yes, sir is also here.
Okay, good.
Sir, good evening.
Good evening.
Good evening, sir. Meghna.
Mhm.
Dr. Ankit, Malaya is also here.
Yes, yes, I know Dr. Millard. Yeah, nice to see. Yeah. So I think many participants joined.
Yeah, we had total 159. We'll wait for some more time. And
Mhm.
our directors will also join. Our deans will join. So I think IGS President Dr. Anil also just joined.
Mhm.
Good evening, Dr. Anil. Good evening.
Yeah, good evening, William.
Good evening,
He is
Dr.
very
Anil.
busy, but in spite, he make time for this.
Yeah. Good
All
evening,
set to
Dr.
start.
Yeah, we are just waiting because some more people will join.
Yeah.
So we had 159 total registered participants.
Okay. We'll wait.
So you are in Hyderabad.
Yeah, I am in Hyderabad. Our council, National Council of Institution of Engineers India is going on. So I jump out of that meeting to attend the inaugural program here.
It's a very short inaugural, so we
Yeah,
can
yeah,
finish
fine. It's all right. So we have a long agenda. 2 days we are here. The entire council runs like that. It's a 3-day program for the National Council.
Mhm.
So I know that ESI, that road, no, Gachibowli Road.
Yeah,
So
yeah.
my house is
Yeah.
very near to that place.
Okay.
So Reddy sir, can you check your audio? मेघना एक बार सर को फोन लगा दो.
Sure, ma'am.
Dr. Ashutosh, Dr. Anil is a national president. Dr. Anil Ashutosh is my colleague at IIT Indore. He works in basically waste management, solid waste management and other
Okay.
things.
Hello, Dr. Ashutosh.
Hello, Professor Dr. Anil. How are you, sir?
I'm fine.
Great, great. Feeling great to join this, this platform through man, meeting such great people.
Anil is our dynamic president who is leading it like so nicely.
Good afternoon, Krishna Reddy sir. You are muted, I believe.
How are you, Dr. Anil?
Fine, sir, fine.
Very good. Thanks for joining. So I saw you were in Surat.
Yeah, I was in Surat, then I moved to Hyderabad now.
I
Hyderabad
think,
became the National
my
Council of Institution.
Every day you are in a
I
different
think our
city.
sir also joined, director sir.
Yes.
1 second, sir. I'll just checking it up.
Hi, Ankit.
Hello, sir. Yes.
So where are you today?
Back to China. Yeah.
Oh, you're in China. Back.
Yes, yes. Yesterday I was in Hong Kong and yeah. Yesterday late night I came.
Very short trip then.
Yes, yes. Because now it's more easy to come through Hong Kong, to go through Hong Kong. To China.
Right,
Yeah.
right.
So have you been to Hong Kong?
Yeah, I've been several times.
Okay. There's from
University of, I went to University of Hong Kong and Hong Kong University of Science and Technology.
Okay.
I know your advisor.
Okay. That's a job.
Good evening, Dr. AP.
Good afternoon, everybody. Hi, Dr. Singh. I am audible.
Yes.
Yeah,
Good
you are
afternoon,
audible.
all.
Yeah.
You are audible.
Very nice to see all the faces which we have seen few days back. Professor Reddy, good afternoon. Yeah, good afternoon, sir. How are you? I'm fine.
I think Supriya also joined.
Good afternoon, ma'am. Good afternoon, all.
Yeah. Good evening.
Our all-time mobile president is also available. Join. It's, I have to admire his patience. Present everywhere, all the time. It's nice. It's nice. Hi, Supriya. How are you?
Hello, sir. I'm fine.
Supriya.
So just a few minutes, we'll start.
75.
Good evening, sir.
Good evening.
So,
Good afternoon. Yeah.
sir, thanks for joining. So we have been waiting for you. We'll start the inaugural.
Oh, really? Okay. Okay.
Sir, we have our speakers also, and also IGS National President, Dr. Anil Joseph here, along with our
Okay.
Vajra faculty, Professor Reddy. So thank you so much, sir, for joining.
Okay.
So good evening, everyone, and we'll start the inaugural because in spite of very busy schedules, I could get some time from our director, sir, Professor Joshi, and who have been very encouraging to all of us in the last 1 year to do a lot of activities. So thank you so much, sir. And I welcome you again virtually to all the participants to this 5 days workshop on sustainable geoenvironmental engineering, where we are trying to cover every aspect of starting from hazard mitigation and also the remedial measures.
Okay.
So I welcome all the speakers and our Vajra faculty especially, and IGO's National President and the Honorary Secretary also for this inaugural event, along with all the participants. So we have almost like 159 registered participants. Since we try to make it a very short inaugural, and immediately we'll start with our lectures. This particular topic is very, very crucial, as we know that there's such a response from the participants, wherein like we try to close it off at the end, because there are so many aspects wherein like the conventional methods are not, like we cannot proceed with the conventional ground improvement and other approaches. In the present scenario, we know how much difficult it is for the landfills and the solid waste management, and a lot of nature-based approaches are coming up, wherein there's some of the new research is going on, where we would like to discuss those aspects in the coming 5 days. So I hope we have a very good time. So with this brief in welcoming note with all of you, I kindly request our director, Professor Suhas Joshi, to kindly say a few words in the inaugural. Sir.
Yeah, thank you, Dr. Nilima. Thank you for inviting me. And Dr. Anil Joseph and Dr. Reddy, thank you for sparing your time. So this is a 5-day program on sustainable geoenvironmental practices. I don't understand much, but as a layman, we are doing a lot of things in the institute to promote the sustainability in the environment, water, and climate. And first and foremost is that we have 200 acres of forest land in our institute land. So out of 500 acres of land, 200 acres is a preserved forest, and we cannot touch that forest. We have to preserve, we have to nurture. So we are doing a lot of activities for making this forest better, livable, and diversify. There should be a diversity, biodiversity in the forest. So we are making water bodies in the forest. We are making the some kind of observation points, birds observation points in the forest, and there are several things which we are working on this forest. So what I mean is that for all your experiments considering geotechnical engineering and whatever you plan, you have a ready-made experimental, what I can say, setup here. Our forest is a ready-made experimental setup for your experimentation. You all can come here, visit us, join some kind of if you want to do some experiments or improve this forest, or help us in nurturing the forest in a better possible way. We have one biggest difficulty which we face is about the forest fire, and every summer we have at least once there is a forest fire, and we spend a lot of efforts in controlling or mitigating those fires and stopping the fires in the later further. So that's also another way by which you can perform experiments. You want to do a survey, drone survey, you want to do something on experiments on soils. Yes, we are all here. It is possible in our experimental forest. So it is a vital area today's times, preserving environment, preserving the climate, and associated disasters. It's a preventing disasters. I would say it's a very contemporary area, and I can see that more than 100 faculty, the participants are there. It's good that you are developing a first level information about the sustainability and trying to teach and educate participants in that direction. We also have started, probably Professor Nilima will talk to you about it. We also have starting a program on MTech in water and climate in the coming July 2023 onwards. Water and climate sustainability program, which is an MTech program. Admission will be through gate examination for this program. Maybe Professor Nilima, I would request you to, at some point of time, present the whole structure of the program to the participants and get their feedback. Yeah, that is a very important program which we have started. In fact, we could have started something in Geotech also, but we have very less faculty members at this moment. So we are looking forward to that a kind of a bigger program which we would like to start on environmental or water or sustainability, so that all the specializations in civil department can come together and join together. So it's a very interesting topic, interesting program. I am sure Professor Nilima is the expert from our side, and she will do a great job in educating and helping you learn the basics about these sustainability of environment. So with this, I wish all of you a very great success in these 5 days and hope it will be useful to all of you. Please do visit our institute after the program or sometime during the program and help us in making this forest more live worthy, so the animal should find that bird should find that it should be worthy living here. Thank you very much and all the best.
Thank you so much, sir, for all the information and such a nice words to start it and motivating us. Thank you so much, sir. So to all the participants, actually, we are doing this event as a part of Vajra scheme, where we have our Professor Krishna Reddy from University of Illinois, so who is visiting us, who is in our campus at present. So I used to get huge support from our Dean R&D, Dr. Professor Pallani. So, because in spite of his busy schedules, he also could join. So I request Professor Pallani to just a few words, because I don't know, for whatever reason, like anything related to R&D, he is a big support for all of us. So Professor Pallani.
Yeah, thank you very much, Madam, for inviting me to this forum. So this is a wonderful forum where I could see a huge amount of participants over here. So as Director Sir rightly pointed out, so we have a strong ecosystem in this, not only in this domain, in various other domains also. So as far as in this domain is concerned, so we have quite a good amount of projects secured from different funding agencies as well as from different consultancies also. And Professor Nilima Madam, regularly she conducts short-term course in this particular domain. So that is what I understand, that more amount of participants, it's a kind of an outreach activity she has been doing it for a long. And more amount of participants are also appearing for this program due to this regular interactions. So on behalf of the institute, so I welcome you to this program. So if time permits, you can also visit our campus. So we have a very good campus, and there is a good infrastructure which has been established at IIT Indore. So you can get an opportunity to visit those infrastructures. So without taking much of your time, thank you very much, and I wish you all the best for this program.
Thank you so much, Professor Pallani. So next we have, we are doing this event along with the Indian Geotechnical Society, which is celebrating 75th year this year. And as a part of National Executive Committee, where I'm part of that committee. So we have our national president also. So I'm doing this event in association with IGS. So IGS is a very vibrant society with almost 6,000 members and 50 local chapters in the country. And so I request Dr. Anil to say a few words to start our
Good afternoon,
program.
all. It's a great pleasure to be part of this inaugural function, where a very important aspect is being covered, the geo-environmental aspects, which is the future of the industry, and hazard prevention or mitigation. So that is the future. And we have a very eminent panel of experts headed by Krishna Reddy sir from University of Illinois, Ankit, Nilima, and a wonderful panel is there to disseminate the knowledge in the next 5 days in the Vajra program. I congratulate Nilima and team for organizing this event and would like to thank Krishna Reddy sir, Ankit, and all the other faculty who have come over for this program and who will be the resource persons. And also I would like to thank IIT Indore director and the entire team there who is supporting all the activities. And Nilima is a live wire in our organization. She is heading almost any activities we say, she is there in front, and she's a big pillar of support in the Indian Geotechnical Society. And she really been communicating, believing in making things happen and to disseminate the knowledge. I know for all the participants, it will be a very useful experience and enriching experience in the next 5 days. You will go out after this training program, will be more prepared to take up the challenges which is in the future. And I wish all the very best for the program. And I would also like to acknowledge the presence of Dr. A.P. Singh, our Secretary of the Indian Geotechnical Society, in this meeting. And there are a lot many people whom we know are there. And now I know this will be an enriching experience. And once again, I thank Krishna Reddy sir for taking the lead, coming all the way from there and doing this program, and Nilima for coordinating this. All the very best for this event.
Thank you so much, Dr. Anil. So we want to, we plan in such a way that we'll have a very short inaugural, and so that we can have more interaction with our speakers and on the problems that you are facing. So it is basically the entire program is more of interactive mode. And as like Professor Reddy sir is involved for several years and such a leader in the whole like on this particular aspect of geoenvironmental, because I started this area after discussing with him on the Indo-US project, etc. So I'm very thankful to Professor Krishna Reddy. Sir, you would like to say a few words? Reddy sir?
Yeah, I think I will have a lot. I will be talking a lot during the 5 days, so I want to keep it minimum. And again, I want to thank Professor Neelima for initiating this Vajra program and making me come over here and designing this excellent program. I think it will be very beneficial to all our geotechnical and geoenvironmental, even all broad civil engineering professionals and students. And I also want to take this opportunity to thank IIT Indore and their administration, director, research R&D, dean, and everybody here kind of supporting these kind of programs that is benefiting students and professionals all over, and at the same time bringing high visibility to IIT Indore. Again, I want to congratulate everyone at IIT Indore. And I've been here for the last few days. It's a beautiful campus. Again, this occasion has given me the opportunity to experience the campus and also meet a lot of faculty here. So with that brief notes, I will be talking a lot as we go through. So I appreciate also, IGS, Dr. Anil, Dr. AP Singh for their support. So with that one, I yield it back to you, Neelima.
Thank you so much, sir. Actually, our Dean International, Professor Sonwane, could not attend. So actually, he supported a lot in this, and his team supported me a lot in this Vajra program, because it was a new scheme, so I had a lot of doubts. So he was really supporting for us. Actually, IIT Indore is having a very beautiful campus, but unfortunately, we could not host so many people, so I made it online mode. But I have please consider this as an open invitation to all the participants, because most of the participants are from different IITs, NITs, and several research scholars from across the country. I think we have almost 22 participants from 22 states, starting from Tripura to every side of so this itself shows that the topic is so much relevant in the present scenario, both in the research and industry. So kindly consider this whenever you are visiting Indore. Indore is a great place, and IIT Indore is a beautiful campus. So please visit us. And I'll be always personally, I'll be always happy to have interaction with all of you anytime. So with that, just a concluding thing, I request Dr. AP Singh, who is a honorary secretary, because this is our 75th year of celebration for the society. And so just to say a few words, because I know most of you are also members of IGS, might be student members and other faculty. So Dr. AP.
Good afternoon, everybody. It's really a matter of privilege and pride for all of us that Civil Engineering Department of IIT Indore is organizing 5 days workshop on sustainable geo-environmental practices, hazard mitigation and environmental protection. At this time, I can say with a lot of population pressure on the earth, it's a really a requirement of the time and just to maintain our globe, so that from environmental point of view, it is sustainable, and not only sustainable, but it is able to cater the huge expansion of population. So this workshop is a part of Diamond Jubilee celebration of Indian Geotechnical Society, which is going to complete its 75 years of its formation. So on behalf of entire Indian Geotechnical Society, I congratulate the organizers of this workshop, Professor Neelima Satyam and her team, and wish a grand success of the workshop. And I appeal to all the participants to become a life member of Indian Geotechnical Society, so that our fraternity become very large and conspicuous on the global scenario. Thank you very much.
Thank you so much, Dr. AP. So with this, I'll just conclude the inaugural session. Along with me, my colleague, Dr. Ashutosh Mandape is also here. So on behalf of Dr. Ashutosh and myself and my staff and my student team, so I sincerely thank everyone. First of all, I extend my sincere thanks to our director, sir, because he is having a lot of meetings and in spite of his very, very busy schedule, so he could spare some time. So it's very encouraging for us if you could join.
Thank you.
Thank you so
Thank
much.
you.
And, Professor Palani. Thank you, sir. Professor Palani also. And I also thank though our Dean International Professor Avinash is not here. So I would like to extend sincere thanks to both R&D section and Dean R&D and International Office and Professor Sonwani also. And I also thank Dr. Anil and Dr. AP from IGS who extend every support because the Zoom platform and other administrative supports and everything they provide me for every activity of IGS, because IGS is very close to me because I was a member since my students in the last 20 years. And I could get an opportunity to contribute to the IGS also. So thank you so much, Dr. Anil and Dr. AP. And my sincere thanks to all the speakers. We have Dr. Supriya from BHU, Dr. Ankit from Shanto University, and Dr. Ashutosh Mandape, my colleague from IT Indore, Dr. Meghna Sharma, so was my former student and a DST Inspire Fellow, to accept this and be part of this event. And we would, as I said, like we have like a very good participation from industry, including Keller. We have participation from research scholars. So from very top company like Keller to research scholars from across all IITs and IITs, NITs, and other private institutions. Also we have. But this is a very good mix that we have it. So let's have a fruitful discussion. I would request all the participants to participate in this interactive session for the next 5 days. And let's start the session. With this, I'll close the inaugural. So I thank again all the people who have accepted my request and joined for the inaugural. So thank you so much, everyone. Thank you,
Thank
sir.
you. Thank you.
Thank you so
All
much.
the best.
Thank
Thank
you,
you.
Thank you.
So we'll
Thank you.
start our sessions. So hope like you already had the detailed schedule. So we are starting actually a bit early, but still like as Professor Reddy, want a more interactive, and I would like personally, I would like to listen to him as much as possible so that I can at least understand, because as I said, like I started this area, Meghna was our student whom I could take along with the sir. And it's not like Meghna who got a guidance, sir. It's like more I got guidance from you. So it was such a nice working with you, on that particular area, because that was new area which I ventured maybe 5 years back. So that we'll start the session. We have our first speaker, Dr. Ankit here, Dr. Ankit Gar. So I request Dr. Meghna to introduce Dr. Ankit Gar.
Hello, I'm Nikhil from Geotechnical Lab and from IT Indore. I would like to call Dr. Ankit Garg, sir. Sir is currently Associate Professor at Guangdong Engineering Center for Structure Safety and Health Monitoring at Shanghai University, China. Sir was a former Assistant Professor at IIT Guwahati between 2015 and 2017, and also part of two-time World Bank consultant between 2016 and 17 for monitoring transport infrastructure project in Assam and India. Sir has research focuses on development and utilization of sustainable materials, including vegetation of soil remediation. He has also awarded Telford Premium Prize from British Civil Engineers Association for his publication in Geotechnical at UK. Sir has research group which has been reported by Kepros Martinez et al. In 2020 as leading group for the greatest number of publications during years 2009 and 19. Sir is currently serves as the associate editor in various journals in Springer Nature, such as Journal of Smart Construction and Sustainable Cities, as well as Journal of Actus Geophysica and Journal of Material Circular Economy. Besides, he was also awarded Young Doctor Award and Youth Talented Scientist Award from Ministry of Science and Technology at China. Sir has been awarded Outstanding Talent Award from Shanghai University. He has been previously appointed as visiting faculties at university in Russia and Macau, and also delivered lectures at Gifu University in Japan, Ruhr University in Germany, ITMO University, Russia, and University of Leeds, UK. Sir, I would like to call you and you can start the session. Thank you.
Thank you, Kunal, for introduction. First, I would like to. My voice is audible, right? I mean, just to ask if it's audible.
Yes, you are audible.
Okay. So first, I would like to congratulate Professor Neelima for organizing this I think wonderful workshop that focus on very emerging topics, specifically in geoenvironmental engineering. And I hope participants, which includes young scholars from, I mean, different places and universities, I hope they can grasp and learn some of the important things that could be there in 5 days. Yeah, and I hope it can help them in their research career in future. Yeah, and yes, so Professor Neelima and me, we have been cooperating for past 1 or 2 years, and it has been quite, I mean, a learning experience also for me, and I am also grateful for her efforts. I mean, everywhere, in not only in editorial boards in journals, but also, I mean, having some of the excellent scholars, I mean, in her lab. Yeah. So I would start my lecture now. So this lecture is more about, I would say, related to my research that was mentioned in introduction about vegetation and also biochar. Okay. So yeah. Yes. So as seen from the topic itself, I mean, I will be talking about two aspects, biochar and vegetation. So biochar, we'll explain later in detail what is biochar. I mean, generally, I mean, the material looks like charcoal, but it's not charcoal. And vegetation, we all know. So one of the aspect in geoenvironmental engineering, I think also directors have mentioned regarding how we need to preserve ecology. So in geoenvironmental engineering also there has been a lot of research that has been done to promote nature-based solutions for their application to solve certain problems. So before I go in detail, I'll just give you a little bit more idea about Shanto. So Shanto is not that popular name like in China. We know Shanghai, Beijing. I'm sure you might have heard quite a lot. Shanto is not that popular, but still, to give you idea, it's located just 2.5 hours from Hong Kong by bullet train. It's more convenient to go through Hong Kong because Hong Kong have many direct flights with other countries. And then from Hong Kong, it's very convenient to take a bullet train in 2.5 hours you will reach Shantou. So they have a direct bullet train from Hong Kong, which you can catch it from inside of Hong Kong. And usually for Hong Kong, we don't need a visa for Indian citizens, so it's quite convenient that we can travel to Hong Kong. Yeah. And this is our campus. It's a newly built campus. I would say we have now two campuses. This campus is the East Coast campus, which is newly built. This was actually meant for hosting also Youth Asian Games. And it's located on the coastal side. We also have, Shanto University is also specifically known for being international. We have a joint independent campus, I would say, with Guangdong Technion Israel Institute of Technology. Actually, the chancellor of this campus, I mean, the first chancellor, not now, the first founding chancellor was a Nobel laureate from Israel. So, so we have a lot of internationalization in the campus that focus on, not only international faculties, but also having joint campus, which is completely independent. Yeah. And we have joint biomedical engineering program with University of Michigan, USA, and this one also have, the academic curriculum, and also there are a lot of visiting faculties from University of Michigan that help to designed this curriculum and I'll also run it. In our geotechnical team, our team is usually led by Professor Shansi Wong. I mean, he's also a dean of College of Engineering of Shanto University, and he's also in editorial boards in reputed journals like Canadian Geotechnical Journal and Geotextile and He's also we recently started this journal at Shanto University. It's a journal of smart cities and sustainable construction. I think Professor Nilima is also in the editorial board of this journal. Yeah, we also have faculties from Italy, Egypt, and Canada. Yeah. So time to time, I mean, this is for young scholars, we invite students from, I mean, before COVID, it was quite common to invite students from different countries, especially in different IITs, to visit our university for either a short-term exchange for research or long-term exchange. And it has been a quite good experience, especially before COVID. But now, since travel restrictions are more or less over and it's stable, it's I think still quite convenient to visit and do some research for short-term or long-term exchange. And give you some idea about facilities. We have worked in wind tunnel facility where actually, if you look at the left side, so this is we call it green forest or vertical forest, we call it. So this is a high-rise building. The concept was designed in Italy. They already have a building, but in Shanghai now they are constructing this building we call vertical forest. So in each balcony, we are talking about maybe more than 100 trees, okay, roughly. It's not small gardens, but it's kind of densely populated forest in balconies. And these are vertical means the buildings which are over 100-meter high, tall. And we also have greenhouse where we conduct research related to vegetation and biochar. And this wind tunnel facility is also being used for consultancy work for a lot of entertainment or resort facilities. And we also built an in-house wind tunnel. This is only for doing research related to near surface of soil. So we all know that the wind do have an impact on evaporation from the soil. So one can study effect of evaporation and cracking under different wind pattern conditions. Okay, so I also like to thank Professor Nilima. I mean, that's one of the very important collaborator, and also other collaborators from IIT Guwahati, Auckland University, China, and also UK. So as I suggested, I mentioned in my in my title that I'll be talking about two main aspects. So I will be slowly taking you to understand this topic. One is on biochar. Okay. So it's basically a material which we used in the soil to modify some of its properties. Okay. It could be, water retention properties, permeability, or infiltration. I mean, these properties mainly. Other part is vegetation part. In the vegetation part, in this presentation, I will be mainly discussing on one aspect. So wilting point generally refers to, like, you can say when plant tends to die, okay, or cease or stops transpiration. I am not using the word die, it's scientific. So when plants stop transpiring or stop taking any water from roots, okay, how we can use unsaturated soil mechanics to define this point. Now, this point is very critical in any green infrastructure. Okay. Now, when we want to design green infrastructure from engineering aspect or want to include plants as an element in our design, we must be worried about, it's time when the plants may not survive, okay, because it's required for maintenance. And we also want that maintenance should be as minimum as possible. Okay. So the selection of plants, I would say the selection of appropriate plants or suitable plants depends on its ability to survive, the first thing. And usually in agriculture or plant physiologists, they are very expert they're quite expert, I would say, in understanding the wilting point from transpiration point of view. But as an engineer, we don't understand in what particular soil, because our conditions are very different from agriculture or from or you can say natural forest. We have a compacted soil which is highly dense. We often don't make use of fertilizers. So, I mean, if we talk about our engineering slopes, man-made slopes, for them, if you have to recommend any vegetation, we need a very specific, very scientific evidence to find that, okay, this vegetation can survive beyond this particular soil moisture. I mean, if the soil moisture go below this particular level, this vegetation is more able to survive better than the other one. Because we are more worried about conditions when the soil is very dry, especially for. So that's why in the third part, I will be mostly focusing on how we can use unsaturated soil mechanics to define this point, which will be quite useful in making selection of appropriate vegetation for using green infrastructure. So, as one of the important, infrastructure that we always have in geoenvironmental engineering is landfill cover. So landfills, they have been very old landfills also in many countries, not only in UK, which have prone to cracking or degradation of the top layer. So I mean, this have effect not only on from leaching or from infiltration, but also it can be harmful to ecology. So in order to rehabilitate this landfill, so there was a project in UK where they promote use of green infrastructure to amend the top covers. And this has been also termed in, named as bioengineered geotechnical infrastructure. If you see on the left side, on the right side, so there are slopes, on the left side is picture from Hong Kong, but you see there's a lot of concreting, but even inside this concreting, there are holes through which the vegetation has been grown. And on the right side is purely green cover for protection from mainly from erosion. And regarding this green infrastructure, there are a lot of, as I think directors are also mentioned in the beginning, that there is also a need to look at the forest. But during this, I would say, urge or need of development that we need in a society, there's a lot of, times that when we have to cut down forests or we have to grow, we have to make our urban infrastructure. So there are something called, we call it eco parks. Now, these are not only useful from ecology point of view, but also it helps to manage a lot of times stormwater. So there are projects in China which has been implemented. We call it sponge city project. It's an equivalent, we can call it green infrastructure, which is a common term used quite in UK and Europe. So this green infrastructure, the main aim is to manage stormwater, especially during flooding, and also at the same time provide, improvement in mental health, and also provide some sort of entertainment or recreation facility for young people and also elder people. So this is how the sites have been converted. So you can see there are different elements involved. You have rain garden, you have the permeable pavements, you have wetlands, it's artificial. So they are created not only to treat soil or water, but also, as I said, for recreational facility. So these have been already implemented in many cities in China. And from my personal experience, I think this is quite useful for elderly people. Because we have in our societies in India, some of the expensive societies, they have some kind of gardens and all, but this kind of eco parks, they also promote ecotourism. A lot of tourists, they come to see this kind of eco parks, and also it helps elderly people for the improvement in their mental health. So now going to the geotechnical part, we have seen the how the system can be implemented. overall have been done, but now we have to understand from the scientific point of view, at least from one aspect in geotechnical, how vegetation, okay, as you see on the left side, or biochar can help to enhance some of our geotechnical properties. So if you look at the equation below, so this is the shear strength of soil. Usually it's an extended Moore-Coulomb equation, which is quite commonly used in unsaturated soil mechanics. So there is a term called soil suction. Now this term is we generally refer to also as apparent cohesion, because it is generated, this cohesion is because of soil suction. And this suction is basically a tensile force, which holds the soil particles together. And this is purely due to this air-water interface. Okay. I will show you. So it's very simple. And if you understand capillary phenomena, this is very not difficult to understand that where this suction comes from. And when we talk about this hybrid cover, we can also promote use of fibers to provide strength, because biochar has been used in literature for improving hydraulic properties, but in terms of mechanical aspect, it may not be quite useful. So we can think of promoting, biochar and vegetation together to enhance soil properties. Soil suction, I gave a very simple demonstration here. Using this picture. This picture is of okay. So this picture on the left side is of is a sand castle, and this sand castle, if you ask, you might have seen, if you have been to the beach many times, that the sand castle is there, or kids are playing with sand and trying to make some kind of small castles. Now the real question is how it can stand 90 degrees, right? So this can stand itself, right, vertically, and this is purely from sand. So I'm sure there is no true cohesion or cementation, but now it could stand vertically because of soil suction, because of there is air-water interface between soil pores, and which helps to hold the soil particles together. So it is because of this soil suction that it could stand. And also here, if you see an insect, it could also stand on water because there is an air-water interface. Now this air-water interface helps to generate, we can call it suction, or the suction force which exists between this air-water interface, which helps to hold this insect. So it's a very thin layer. It's a very thin layer. I would say it's a very thin layer, air-water interface, but it's very strong. So the strength is coming also from this very thin layer of air-water interface. Okay. So the idea is basically to hold the soil particles together, increases the strength of soil. Now, if you add too much water, you will realize that you will experience also that the sand castle will fail. Okay, if you add too much water, or if it is completely dry, assuming there is no moisture, then also you cannot build a sand castle. You cannot build it from a very dry sand, right? You can only build it from a sand which has some moisture in it. So this is about soil suction. Now, the reason why we are using biochar and vegetation is we are hoping or we are hypothesizing that there could be an enhancement in soil suction or water retention property by using these two, vegetation or biochar. Okay. So that's the main hypothesis. So biochar, now coming to scientific definition, it's a solid material obtained from thermochemical conversion. This temperature may be not very, always 700 degrees, it can even cross 700 degrees Celsius. But generally, most of the biochar that we get in market, they are manufactured at between 300 to 700. In the main point, this is an oxygen limited environment. Okay. So if you look at the biochar, I mean, very much look like charcoal, okay, but you can find in physical way form. It can be in terms of pellets. It can be in terms of, you can crush it to make powder, okay, depending on, I mean, how you want to use it. Then chemically it looks like this. So they have a porous structure, and also these groups. Okay. Now these groups are responsible. Some of them are hydrophobic or some of them are hydrophilic. So they can also attract water towards it. Okay. So these two are one of the main functions. And some of the functional group, they have been used in literature for absorption of contaminants, okay, from the soil or even from the wastewater. So biochar is not a new material, but it has been used, as I said, extensively in, I mean, for agriculture or soil contaminant absorption or even for water treatment. One of the important aspect that we can think of, or we have a motivation also to use biochar, is because we are trying to promote a circular carbon economy where our waste can be reused or can be recycled into something valuable that can be again used for, I mean, important aspect or application like infrastructure. So in a circular carbon economy, the waste is reused or recycled back into production. Okay. So in the linear economy, it was like this, but in a circular carbon economy, it's in this way. So this concept, I think, is quite emphasized by governments in many countries, including China and India. And this is one basic also related to why we intend to use biochar. Okay, so one of the very basic, I would say, is also demonstrate, you can say, suction. Okay, so this I was talking to you about the solid soil. We generally comprise of, you know, air, water, mineral, and then there is something called air-water interface. Okay, and this capillary water represents the water retention that we have in the pores of soil, and we assume that this water is retained in form of cylindrical tubes, okay, with diameter d. Okay, so, and this surface tension, it's Ts. So if I think you all know how to derive this equation. So if you derive, you will know that the capillary head is actually inversely proportional to the diameter of it. So if you have a larger force in the soil, your water retention height will be less. So for sandy soils compared to clay soils, so we expect water retention to be less in sandy soil as compared to a clay soil. Okay, so biochar, we expect that the pores are much finer as compared to, I mean, most of the sandy soils. So we can expect that we are trying to reduce the pore size in a soil so that it can retain more water. So this is physical change, but there is also chemical changes. As I said, biochar have functional groups, okay, which is much more complex than what I have shown in the equation. So, but this equation is the most basic one to understand. Okay, with the presence of biochar material in most of the sandy soils or silty soil, there could be increase in water retention. Okay, so because the biochar diameter is smaller, so the chances of HC of biochar could be higher than soil. And when we talk about water retention curve, this is very important. In unsaturated soil mechanics, we often represent, ability to retain water in a porous material. So biochar is a porous material, soil is also a porous material. So any porous material have this water retention characteristic. Okay? Even I think for young students, just to tell you, towel. Okay, so towel, when we take shower, we use towel to, you know, remove moisture from our body, right? So towel also is a porous material. It also have a water retention characteristic. Soil also have a water retention characteristic. Biochar also have a water retention. So every porous material have this curve. It's not just only related to soil. So, I mean, if we look at this curve, okay, this is a saturated water content. You have a dry the water content at a very dry state. Okay, so this region mostly near saturated region. I don't say it's fully saturated, but nearly saturated. And this region is where, your suction crosses the air entry valve. Okay, and this region we assume there's air. Before that, before this point, we assume there is no air, but in reality, air is always there. Okay, so when we talk about using biochar, one of the intention is, okay, especially in this dry region. So we know this residual water content. If we, I'm hoping if we can use biochar, increase this residual water content, because this is most critical for most of the, vegetation that is growing in the green infrastructure. Okay? Because we don't want to, put so much maintenance in irrigating, green infrastructure every time. So we can think of using some enhanced modifiers that can improve the residual water content, okay, at this time. So biochars have been used in other no applications, but in green infrastructure, it's still limited. And the reason why we need a specific research for this is, as I told you before, that our conditions are very different from that in agriculture. We have to think about strength. We have to minimize use of additives. We expect there is no irrigation, because also our design period when we design any green infrastructure, including for geoenvironmental infrastructure, our design period is much longer. For agriculture, they need to harvest it, and they also care only shallow layers of soil, not, they don't go much deeper. So, and also amendment ratio for agriculture is usually 0 to 5%. But as we did our research, we found biochar is mostly an alkaline material. So adding excess biochar can increase pH, can also cause issue to vegetation. So we don't know what amendment ratio can suit our engineered slopes. Okay? Not just slope, but very specifically what type of soil, what type of biochar we need. So all these questions need to be answered. And there has been a lot of research in literature. I would say Professor Reddy sir have done a significant research on use of biochar applications in landfills, and also there has been research related to applications in unsaturated soil mechanics. However, there's limited scope of attention that was paid in understanding how the production process of biochar. Now, this is important because at this point, we don't treat every biochar as same. Every biochar we assume is different because the production process is different. So because when we do research, if we buy biochar from the market and we try to do research, we may not be able to understand its mechanism properly, because the biochar that is available in market, they don't have specific details of how it was produced. Okay. So production process, there are two things which are very important. One is the pyrolysis temperature. Okay, so this is very important, and one is the feedstock type. Okay, so whether it's plant-based or animal-based, even in plant-based there could be different types. So these two are very important. At what temperature it was produced. So when you change this temperature, your biochar, this properties changes quite significantly. So first, I will give you a small demonstration to give you idea how a biochar can influence water retention. And second is the cracking property. Okay. So these two things I will be sharing. So for this, we did a small experiment in the greenhouse rooftop. We designed this one-dimensional box where you can install the suction sensors to measure soil suction and also water content. And we were also we subjected this pot to 9 or 7 drying wetting cycles, which includes the artificial ponding followed by drying, ponding. And we also measured cracking. During the drying process, the soil will be subjected to crack. So we use image analysis to capture the cracking. And the biochar that we use for our research till now is we mainly use from water hyacinth weed. It's quite common also in India. This one is basically an invasive weed. When I say invasive, it means it can kill other plants and can capture the whole area. We also did some research using algae because Shanto is a coastal region. But in this presentation, I will be presenting mainly from water hyacinth wheat. And to give you more idea, this is biochar produced at 350. This is at 550. You can see this biochar is much more porous as compared to one at 350. So if you consider the temperature effect, you can appreciate that, okay, if it's more porous, your suction should increase, right? Water retention. But there is also one issue. When you increase the temperature of, how to produce biochar, you are also destroying the functional groups. Okay, so there could be an issue that the functional groups, number of functional groups can be reduced with increasing the temperature, though you are increasing porosity. So I'm not going through the results in detail, but just to give you idea here, this is we measured water retention curve, unsaturated soil water retention curve, and also cracking. So unsaturated soil and cracking. So we measure two parameters. So you can see one is theta, is a function of suction, and this one is cracking. Okay, this CIF is cracking. Okay, it's also a function of suction. So this orange dots represents CIF of cracking. This blue one represents water content. Okay. Just take this example. Okay, so if you look at the minimum water content, it's around 15, and this one for 10% biochar. So BC is 10% biochar. It has increased from 15 to almost 20. So the water retention increased from 30 to 48, okay, and minimum water content, which is we are more focused on minimum water content. I told you because we are more worried during the dry condition. It's almost double with the presence of biochar, and also the cracking reduced. Now, one good factor is now these are very initial results for only 63 days. Okay, you can ask questions: what happens after 630 days, or what may happen after 6,300 days? Now, these are real long-term questions that need to be answered in field. Since our experiments were done in a greenhouse in a small scale, so I okay, is the screen visible? I mean, just to ask.
Yeah, it's visible to me.
Okay. Yeah. So coming back to presentation, so if we talk about the long-term answers, that questions, we need to answer this in the field, because in the field it's our the conditions that we simulate drying and wetting is first of all not artificial. There could be other processes that could be taking place in the field, especially on the slopes. Yeah? There could be erosion taking place at the same time. So there are a lot of questions that need to be answered. But this was the first set of experiments that we did to first establish unsaturated characteristics, okay, and also cracking with respect to biochar. But it has, as I said, a lot of limitation. One major is it was for limited period. Now, when we talk about long term, I don't expect biochar itself to change much. I mean, its own physical chemical structure, because biochar is quite stable material. It is already pyrolyzed. However, its interaction with soil may differ depending on how much rainfall or how much number of drying wetting cycles it may go through. So those are issues that need to be tackled in the long term. Okay. Now, another question which I mentioned was that we shouldn't treat every biochar equal or same. So for this, we picked three different biochars produced from three different material. One is wood, chicken manure is, you can say, animal based. This is again vegetation based. And we use two pyrolysis. So all these biochars we produce in our own lab at Shanto University in a controlled condition. Okay, and we want to know if suppose an engineer asks you what kind of biochar will be more suitable for enhancing water retention in a slope. Suppose the slope is in a very humid region where there is a lot of rainfall, and one of the important concern is about rainfall infiltration. So if we think from that aspect, I mean, we have 3 different biochars. So which one we should use? And also we have 2 different pyrolysis temperatures. So we did this experiment with the intention to understand, okay, which type of biochar can be recommended, okay, maybe, or which can be not recommended, I would say, have a potential to to be used for humid region or dry regions. So for this objective, we used a climate control chamber, and the reason was we want to eliminate any other factors, which could be climate fluctuations, or it could be uncertainty due to very large size of the soil sample. So we want to just focus on one element, which is biochar, and also want to give a controlled climate conditions of drying and wetting. So in here we induce a drying or wetting path using a humidity control chamber. So we use different temperatures and also different biochar content. We also have different density. I haven't shown here. So as I said, humidity first was raised to 90%, which is quite very highly humid. 90% or 80% you can consider maybe a time during rainy season, and 50% could be mostly dry season, maybe during the winter time. Okay. It's very less, 50%. Usually in India, maybe we can get 58, 60%, but 50% is relatively dry, quite dry. So when we simulate wetting, we increase the humidity slowly 10% every time. Okay, we did 7 weeks of monitoring. We also characterize carbon composition for different biochars. You can see, like as expected for wood biochar, at 600 degrees Celsius, your carbon composition is much more than at 300 degrees Celsius, which is expected, because when you have high temperature, your feedstock tend to most of the lignin content tends to convert to carbon. But there are other contents which can be volatile, and also you see water hyacinth biochar also have high carbon content as compared to chicken mint. This is some.
ठीक है, okay, ma'am.
Okay.
No, ma'am, I'll come.
Okay. So we check the water retention. As I said, we simulated drying and wetting cycles. So you can see, okay, I will discuss this graph. So BS represents this bare soil, that is, there is no biochar. Okay. And this one represents the water hyacinth biochar. Okay. I don't want you to focus on all lines, just 2 or 3 lines. So this is important. Okay. So this lines is important. So you see here, we will focus on 2 extremes, okay? Maximum and the minimum. So you see the water hyacinth biochar at 300 degrees Celsius is consistently retaining higher water than the one with bare soil or even other biochar. Second one is water hyacinth biochar at 600 degrees Celsius. Now, very strangely, we were expecting this biochar to perform better, 600 degrees, because higher temperature leads to more carbon content and also more porosity. But we found out that 300 degrees Celsius is more better. Now, the possible reason it could be, as I told you, if you increase temperature, you are also destroying the functional groups. Okay, you are increasing porosity on one hand, which is good, but you're also destroying functional groups. And we have other details which I haven't shown here in this presentation. You can look in the lecture, or you can email. So as I said, our focus of this study was in a very dry range of the soil. Okay, I told you that we are more focused when your green infrastructure is subjected to a lot of drying, period, where there is chances that it can cause problem to, not only cracking on the surface of soil, but also to vegetation. So this study suggests, I didn't show the result, but 10% biochar application rate is useful, and also water hyacinth biochar, which is from the invasive weed, is better in absorbing more water than compared to other biochars. And this is because of the functional groups, okay, which is expected to provide more water retention. Okay, so in also when I talk about implications, so it means when we have to decide about different types of biochars, which one have to be used for water retention purpose, I think the vegetation-based biochar have more tendency to retain water than animal-based biochar. But animal-based biochar have other advantage, especially in terms of contaminant absorption, which is not, I'm discussed here. And the third part is, as I told you, that we need to look into when we talk about application of vegetation in green infrastructure. One of the important concern is when vegetation stops to transpire. So, so there have been observational evidence that we provide how to define. Okay, if I say how to define this point using, unsaturated soil mechanics. So this work we did in collaboration with Professor Shrideep from IIT Guwahati, and this is very interesting because we try to define how this wilting, can be understood from unsaturated soil mechanics. Because in literature, I can tell you, this term came from agriculture. This term came from agriculture, but there is a tendency to use this value, 1500 kb, that at this soil suction, okay, most of the plants will die. Okay? The plants will stop transpiring, or the root water uptake will not be there. Okay? So they will stop transpiration at this soil suction. So this number was used consistently in many literatures have used. So this number came in 1978. Can you imagine? Now we understood the problem because we think in 1978, when agriculture they were using, first of all, there was no instrumentation to measure directly soil suction of this value. Even now, if you have to measure soil suction at very high range, it's not so accurate. We have a lot of limitations. And in 1978, it was almost impossible to measure directly. So when those researchers, they defined this value, they used actually existing water retention curve, which is not a measured one, which is also a predicted one. And they converted water content into suction using that SW, water retention curve, which was itself not measured one. So I could understand, and then this value became a magical number. Many literature, they have been using this number. Now, from an unsaturated soil mechanics, I think we can appreciate more, or even as a layman, we can think that this number cannot be same for all vegetation, and that too, even for same vegetation, even for same soil, it cannot be same because vegetation are genetically different from each other. They have some genetic difference. But even if we assume it should be ideally same for same vegetation, but in different soils, we cannot say that this vegetation will die in clay at this suction and also in sand at same value. This is not possible because plants behave very much like human beings. And one human being, his ability to live without water for several days is very different and might be more or less than the other human being. Right? And also it will depend on the climate. Okay? You can stay without water in a humid climate, maybe for longer period of time than in a dry climate. Right? So even if you think from a layman point of view, this number, we started questioning this number because this number have been used quite consistently. So then we explore, in an objective, susceptibility of a native plant species common to Southeast Asia. And this framework, we say that we introduce a new framework to determine a wilting point by actually measuring the health of a plant. Okay, just like doctors, human beings. Okay, if I explain you, when we go to hospital, sometimes doctor will say, okay, let us check his blood pressure, right? They check our blood pressure, they check our heartbeat. Okay? These are very two basic indicators, okay? That okay, this person is is doing okay. It's not like it's out of control. So blood pressure, heartbeat are very two, and oxygen level. Okay. Third is oxygen level. So just like our human beings, we have indicators, very basic indicators to indicate, okay, this person is in a normal state, is not so abnormal. He's having a normal blood pressure, maybe high or low little bit. Then he has a heartbeat, maybe little high or less, or he has oxygen level, which is okay. So we can say that, okay, this person is surviving, right? Similarly for plant, we also need to represent some health parameters, which actually tells us whether this plant is taking water or not from the, through the roots. And that is why we develop a relation between soil suction, which we geotechnical people understand, and then leaf parameters. Now, these are the leaf parameters, okay? I'm not going in detail, but it's quite commonly used in agriculture. Okay, plant physiologists, they use quite common, but from their side, they are not able to um, establish this relation with soil suction, or they have not been able to represent, this wilting state of a plant through by relating to actual measured soil suction. As I said, from in their mostly research community, maybe 50 years before, there was the instrumentation to measure suction was not developed, was not, I would say, sophisticated. There was some instrumentation, but not sophisticated. So if you talk about stomatal conductance, this is quite similar to, I'm sure you might have learned in your high school or in biology textbooks, or it's quite similar to permeability of soil. In permeability, we say is the ease of which the water flows through the soil pores, right? So here also we say is the ease or the rate at which the water is released to atmosphere through pores in the leaf. Okay, we call it stoma or stomata. Stomata is a singular, stoma is plural, so there are many pores. We call it stoma. So this is one very important aspect. Now plants are very clever. When they know that the water is less in the soil, okay, they will know, they will sense it, and they will close their stoma. They don't want to lose the water in the leaf to atmosphere easily. So plants also regulate their functions according to the water which is present in the soil, and also the climate, the temperature or humidity around it. So just like human beings, okay, if we know that we don't have enough water in our home for next 3 days, we will change our, regular day-to-day habits to preserve that water. We don't want to lose water so easily. Similarly, plants are very clever. That's why plants could live very long life, even though we don't touch them. They can live because they know how to take water from the soil, and when to close their stomata. So this is very much a function of soil suction. Okay, we can even hypothesize. I gave you a simple analogy from human being. Okay, then you have photosystem process. Now this you may not have read in biology textbook, high school. Maybe this one you might have read. They also use for ATP, androgen phosphate production. So photosynthetic process is basically two steps. One is they take, electron is excited, and in other process, they make this NADP. So this is basically for your glucose production. Okay, so one is stomatal conductance, another is photosynthesis process. Okay, so we use this experiments 1D box, but we also use measurements from plant physiologist point of view. So for young scholars, what my experience have suggested us is that it's very important that we learn, when we do multidisciplinary research, it is very important that we should be very open-minded and also try to learn from other disciplines or experts in other disciplines in a more better way. I remember Professor Reddy sir mentioned in the pre-conference that we met that in civil engineers we should not be only working in the soil lab. We should also think about working in microbiology lab or maybe labs in physics. Okay, so there actually you will learn that there are a lot of things which they have done. Okay, so it's already done by them. But I mean, even if we can make use of it in a better way, I mean, it's not like you can directly use it in our field, but you need to think carefully how to use it. But if we can use it carefully with the caution and also by modification, actually we can learn a lot. I mean, in any multidisciplinary topic that we work. So this is for young scholars. Okay, that open mind is very important. Okay, and also try to work in different labs. So, I mean, I did not go through results in detail, but this is process that is basically a result. Okay, this is a result. So, but I have presented in form of a table. There are 5 parameters, 5, 6, 7 parameters. So we have 2 columns, clay, loam, and silty sand, and we quantified drying. Okay, so during the drying process, we actually were measuring water content. This is soil parameter. Stomatal conductance is plant health. Photosynthetic efficiency is also plant health. So I'm using simple terminology, plant health. This is also plant health, plant health, plant health, plant. So what we did is we simultaneously measured soil suction or soil water content with other plant health parameters during this dry process. And then we try to observe at which soil suction suppose your stomatal conductance goes down sharply, like here. So this is photosynthetic efficiency with suction. So we found that at this point, okay, or at this point, there is a sharp reduction, okay, in the photosynthetic efficiency. Similarly, we found here. So these are the point where, you know, doctors, I would say medical doctor will be very careful. Okay, they will be checking your blood pressure or oxygen level. They will be monitoring. That's why, you know, in the hospitals also they do this. They want to check at which point. You know, it's very important. So here also we want to know at what particular point these actual health parameters are going down. Now the suction. Now this suction, we cannot say the suction is uniform in the soil. Now one limitation in the experiment is we assume the average suction around the soil here is similar, or it's an average suction. Okay, but of course suction can be different at different points in the soil. Okay, so you should also be careful that when I'm showing suction, we generally say it's an average value in a small box or near the roots. And corresponding to the points where the reduction is taking place, we can say that this point could be close to the wilting point. Okay, not 1500 kPa, which is taken, you know, in literature quite, I mean, by many researchers. Okay, so what we found for silty sand, actually, which we expect also in the sandy soil or silty sand, your wilting point is much earlier, like 260 kPa. So it means that because sand cannot hold much water, so even at very low suction, the vegetation can wilt. Okay. But in a clay soil, your wilting point is much higher. Okay. So now you can think. Now this is what I was telling you in literature. 1500 kPa was taken as a magic number. Okay, for any wilting point, for any vegetation, it was taken 1500 kilopascal. But what we found from our research is that it depends on actual health parameters of plant. We cannot just take 1500 kPa and use it for any vegetation. And this kind of experiment also give us framework of, suppose we want to select a new plant, or we have 5 plant species, and we want to select which one can be used in our green infrastructure or geoenvironmental engineering infrastructure. We can, based on this set of experiments, we can define, I mean, or from the wilting points, we can define which one have more potential. Of course, we need to also look at other aspects, but wilting point is one of the important aspects. Yeah. So I am not going through detail, but just to give you an idea, we also analyze root architecture in different soils. And we also compare the time till wilting in clay and in silty swine. Okay, because in silty sand there is also an advantage that there is more dissolved oxygen because the pores are weaker, and also root hair formation. We also analyzed leaf, through color change, through visuals, which also help us to give idea of, so only through visuals, we may not get idea. We can get idea that there's some problem with the plant, but not complete. Yeah. So it's an experimental evidence-based research to prove that 1500 kilopascal cannot be used as a magic number. So, for young scholars, I always encourage them when you read any literature or textbook or anything, always try to question things. Even I would be happy if they question things and they come up with more better framework, more better, improvement, because there are a lot of assumptions many times in numbers that we mentioned. So for young scholars, I suggest them that they should always question textbooks and also which literature even is published. And we are just to give you an idea, we are also working on developing some irrigation modules, or it can also regulate water content based on unsaturated soil mechanics. The main part was we are using this function of transpiration and water suction. We are also working on developing some mobile applications for estimating moisture through image analysis. So this image analysis, is based on color analysis principle, which was published already a few years before. But now we are developing some mobile applications which can be used to get a rough idea of soil moisture, but for only certain soils. Okay, these are not applicable for every soil. Yeah. And yeah, so we have some special issues related to, this. Soil plant interaction. Although this journal charged fees, but since we are the special editor, so I can, waive this fee also for some good manuscripts. Okay, so it's about sustainable management, intelligent measurements in soil plant system. Another journal about deep underground science engineering. Professor Nilima was in the editorial board. Okay. So this journal is also open access, but there is no fees. There's no fees for this journal, and I think many scholars from different countries are publishing this. So this is just to give you additional journals idea, which we are part of. So with this, I would like to conclude my presentation. I hope it's you can understand some points, but you're always welcome to discuss, and you can refer to me by email also. Yeah, thanks.
Thank you so much, Ankit sir, for enlightening us on this exploring role of biochar and vegetation in geotechnical engineering. I'm thankful to you, and thank you for accepting our invitation for this workshop. So I would like to request Dr. Ashutosh Mandpe sir to introduce Professor Krishna Reddy sir for the next session. Ashutosh sir.
Hello, am I audible?
Yes, sir, you are audible.
Yes, sir. Yes, sir.
So, yeah, first of all, I would like to welcome you all. I would like to take opportunity to introduce Professor Krishna Reddy. So, as we know, Dr. Krishna Reddy is a university scholar, distinguished researcher, and professor of civil and environmental engineering Director of Sustainable Engineering Research Laboratory, and Director of the Geotechnical and Geoenvironmental Engineering Laboratory at the University of Illinois, Chicago, USA. Dr. Reddy received PhD in Civil Engineering from the Illinois Institute of Technology, Chicago, USA. Dr. Reddy is a registered professional civil engineer and an envisioned sustainability professional. His teaching, research, and consulting expertise includes geotechnical infrastructure systems, environmental pollution control and remediation technologies, waste management and beneficial reuse, and sustainable resilient engineering. Dr. Reddy is the author of 4 major books, including the 2 widely used books. The first one is Geoenvironmental Engineering, Site Remediation, Waste Containment, and Emerging Waste Management Technologies. And another book is Sustainable Engineering, Drivers, Metrics, Tools, and Applications. He is also author of 258 journal papers, 27 edited books, 22 book chapters, and 226 full conference papers. Dr. Reddy has received several awards, including American Society of Civil Engineers, Wesley W. Honor Award, ASTM Hudson Togler Award, UIC Distinguished Researcher Award, University of Illinois Scholar Award, and University of Illinois Award for Excellence in Teaching. He is a registered professional civil engineer, Envision Sustainability Professional, Fellow of American Society of Civil Engineering, Diplomate of Geotechnical Engineering, and Board Certified Environmental Engineer. Now, I would like to request Professor Reddy to please, start his talk.
All right. Thank you so much, Ashutosh. Can you hear me?
Yes, sir. Yes, sir.
Yes,
You're perfectly
sir.
audible, sir.
All right. So, first of all, I want to welcome everyone for this workshop. It's a very unique workshop, 5 days, plenty of time to discuss your concerns, comments, ideas, or whatever help you need. I think, as you know, this, a lot of times you are in a time crunch. I think this workshop will give us enough time to discuss details, and hopefully every one of you can be benefited by this workshop. So as you know, you have received these program brochures, and this topic is very timely. A lot of research needs to be done to address these big issues of hazard mitigation and environmental protection from a sustainability point of view, from resiliency point of view, and to achieve sustainable development goals. Even though we are not talking about, the importance of achieving those sustainable development goals, we are focusing more on technical aspects of, how we can do engineering to address the hazards and address the environmental pollution. So I just want you to keep in mind the broader goal of ours is not just trying to solve a tiny problem and walking away, but we are going to make a huge difference if every one of us does a little bit, and it's going to make a huge global impact. So I really like the title of the workshop. This is, idea of Professor Neelima Satyam. Thanks to her for coming up with this title. And you see the schedule, and we have a first presenter is very young, very dynamic researchers, and followed by me. I want to go a little bit slow, and unlike my other presentations where I may have a very broad audience with not much background, so I tend to be very general. And in these presentations, in this workshop, I want to be a little bit more technical because I can see many attendees are doctoral students or faculty, more involved in research. So I could go into more technical details rather than just giving broad overview of the topic. So I have 5 days of presentations, so hopefully I'm not going to be boring you. We can take the breaks, and if you have any question, you can stop me and we can answer that question and keep going. Or other option is keep writing your questions, and hopefully at the end we will have plenty of time to go through those questions. So just make sure that I want to make sure that these sessions are well spent and very beneficial to you as you pursue your career. So before I get started, again, I wholeheartedly thank Dr. Nilima Satyam for making this happen. It's not easy, to get a Vajra award, and she has been very meticulous in preparing the application and submitting to DST, able to secure this Vajra adjunct professorship for me, which is very competitive, as I understand. As you should know what Vajra stands for. Vajra is Visiting Advanced Joint Research Faculty Scheme. So that's like, I'm a visiting adjunct professor to help undertake advanced joint research. And I was looking at Vajra website, and I was looking at the Prime Minister's message on the Vajra website. It says that this program is to enable NRIs, non-resident Indians, to participate and contribute to research and development in India. So I know I am trying to help of Indian researchers, formally or informally, but recognizing the need for this in a formal way is very heartening to see that at a high level, at a central level. So under this program, a visiting scholar can come and visit for 1 month or 1 to 3 months. But because of this program, I'm here for 1 month. Again, my goal under this program is to kind of help support the research in India. So and as a part of this, IIT Indore has given me adjunct professorship, and I'm able to be here at IIT Indore campus. I want to again thank workshop organizers, Professor Nilima, and all our students and colleagues, Meghna, Ashutosh, Nikhil, Kunal, and all of them involved in this one. And I like speakers who are going to speak on different days, and all of you, trying to find the time. So I hope you can be benefited by this entire program. So many of you know, but some of the names I see are very new to me. So I'm from University of Illinois, Chicago, in USA. And Chicago is an example of what should be an ideal infrastructure and environment should be. And civil and environmental engineers play a major role for realizing all these things. So last 2 slides are my university campus, but civil engineers and environmental engineers make sustainable development and make the quality of life improving every day. So I do a lot of research on different areas, but all of these research areas I can categorize into 2 types. One is the environmental remediation of soil, sediments, groundwater, and stormwater. Some people think that this is more like environmental, but as you will see in my presentations, having a geotechnical engineering background, complementing with some chemistry and biology, you could do much better than typical chemical engineer, or with a chemistry background, or even sometimes environmental engineers who deal with only water, wastewater. So it's all like a geo. You're dealing with the groundwater, you're dealing with the soil, even dealing with the storm water that when it rains, it is on the ground, it is flowing on the ground, and it carries a lot of contaminants with it. So don't think that this environmental remediation is a topic of only environmental engineers. It is, it's a combination of geotechnical and environmental. That's what I call it, geoenvironmental engineering. And the second one, under this, you can see a lot of different technologies I work on. Again, looking at the soils point of view, groundwater point of view, how geo aspects affect the remediation. So on the second area of my expertise is waste management and landfill engineering. As you all know, and you read in the newspapers almost every day about the problems with the dump sites in India. And the problem is going to only increase, not decrease. It's not going to go away. The efforts that are going on now are fragmented, and they're not going to give you holistic, long-term sustainable solutions. So having a good idea about this field, it's not about creating new. You just have to look at what other countries have done it and what could be done in India based on what has been done in other countries. So as simple as that, right? And obviously, what is done in US is not practical to do in India. So it's what are the lessons to be learned? So, just even visiting, the problems that are similar in US versus in India, and seeing how they are addressed and see what can be done in India. So a lot of things about beneficial use of waste materials, landfills, and then from sustainability point of view, how can we make them more sustainable and resilient. So there are a lot of interesting things in this. So I work in this field also. So these are two important areas in geoenvironmental engineering. And I work on life cycle assessment and sustainable and resilient engineering. So this is, everybody uses the words sustainability and resiliency, whether they understand it or not. But I am interested in quantifying the sustainability, quantifying the resiliency. So when you quantify it, you will be able to know whether it is sustainable or not. Otherwise, you will be just arguing all the time that whatever I'm doing is sustainable. But when you crunch the numbers, whatever you thought sustainable may not, you may find a surprise that it's not sustainable. So quantifying sustainability and resiliency important. That has been my focus. And once you have that kind of a quantification frameworks, they can be applied to anything that anybody is doing in engineering field. It could be in geotechnical engineering. It could be standard conventional geotechnical engineering. It could be environmental engineering. It could be transportation engineering. So it's kind of a very broad application of using the quantitative frameworks. So I want everyone to know my background. You can ask me why I switched from conventional geotechniques to geoenvironmental to sustainability. So my undergraduate is in civil engineering, like many of you. My area of interest was structural engineering, but because of my soil mechanics professor, I chose geotechnical engineering for my master's. In Roorkee, I worked on pile foundations, I worked on earth retaining structures. And then when I went to US, I worked on ground improvement, constitutive modeling, geotechnical earthquake engineering. So I covered, I think, most of the broad areas in geotechnical engineering. But after that, I worked in industry for 3 years, and I saw the real need for geoenvironmental solutions. Geotechnical engineers were working on geotechnical problems, and environmental engineers were working mostly on water, air, but the soil and groundwater is kind of neglected. And that is the area that needed a lot of attention. So I moved from conventional geotechniques to geoenvironmental. And another important aspect is that in geoenvironmental, whatever you have done in research today, people are ready to apply tomorrow. Unless in geotechnical engineering, there is always reluctancy. If you talk to people, they will say, "Oh, I've been doing this way for the last 30 years. I'm not going to change." So they are very conservative. But whereas in geoenvironmental engineering, these problems are new, and so we need solutions. So whatever research that you do are applied right away in the field. So that's again, doing research is not, it's important, but it's more important to see your research solving the real world problems. I think you get a lot of satisfaction, right? your research is used and the problem is solved. So, I cannot overemphasize that feelings that I had when my research has been applied and it was shown to be successful. So you do lab research. I mean, you identify a research problem and you come up with the hypothesis, and then you do the bench scale testing in the lab, because that's easy, less expensive, easy to be done. You should have a right equipment in the lab to be able to do that one. And then, that bench scale testing would be the first stage to see, your idea is possible or not. If it doesn't work in a small scale, it's not going to work in a large scale. So this is almost like an initial screening without investing too much time and effort. Then if it works, the scaling effects are very important in our field. So you do the large scale lab testing. So you basically scale up from batch experiments to large column experiments and so forth, and see, if your hypothesis still holds, your solution is still valid. So you understand the fundamentals. So because it's easy to change variables, you can control one thing and keep other things constant, because when you go out to the field and do it, you don't have control on a lot of parameters. So some may argue that lab tests are never going to produce the field conditions. That's true, but you need to understand the fundamentals. By this large scale lab testing, you will understand what the fundamental mechanisms are, and then you have to quantify those through modeling, mathematical modeling. It could be most of the times we resort to numerical modeling, and then once you develop the model that considers all your fundamental mechanisms, then you can use the model to scale up to design the field situations. And then you have to prove out in the field, instead of telling all the engineers, okay, go and use my solution. Instead of that, you should go to the field first and do a small trial experiment in the field and see if it works or not. And if it works, then you have a confidence in recommending that solution to other people. So we go out to the field. So it's a lot of fun for me to work from lab scale to mathematical modeling to the field scale. So you can see the pictures with my students. We have fun, doing all levels, from lab to modeling to the field level. So our motto is fundamental advancements geared towards practical solutions. So we are in the university environment. Many of you may be in the university or maybe doing PhD. Every PhD has to, advance the fundamentals, but all of that should be geared towards the practical solutions to the real world problems. So this is my lab. You need to have a lot of lab equipment. If you don't have it, then you need to find the collaborators who have that can help you to, use their facilities. And then I always show this slide. These are all my research students and scholars. Many of them are from India, many of them from other places, Brazil, China, Turkey, Spain. I mean, I can list on countries. It's always pleasure. I think, as a researcher working in the university, especially a faculty member, as the pleasure of, working with the talented students. So I want to mention all these things up front so that you can know my background and then in the future presentations, I'm not going to repeat these things again. So you can find a lot of our work in these 4 books, Sustainable Engineering, Geoenvironmental Engineering, and more specialized sustainable remediation and electrochemical remediation technologies. So you can go to this website and get all kinds of information about our research. So as I said, I work on geoenvironmental engineering, and this workshop theme is geoenvironmental practices. One should understand the term geoenvironmental and geoenvironmental engineering. I think a lot of people have different opinions about it. But my perspective is geoenvironmental engineering is going to solve the problems related to environmental and sustainability resiliency issues. So from environmental point of view, you need to look at environmental characterization, risk assessment, containment technologies, remediation technologies, waste management, what we want to do in the sustainability in general in geoengineering practices. So those are kind of problems that we solve. In order to solve these problems, you need to have a geotechnical engineering as a background. And then you need to have other additional backgrounds, because a lot of these problems cannot be solved with from knowledge in one particular field. I didn't size this circle in terms of the importance of each field. I try to keep it equal. But geotechnical engineering plays a major role. And then you have environmental engineering. You need to have a geochemistry, microbiology, and then you need to look at these other issues also: environmental justice, economic issues, and systems engineering, looking at the things holistically, not just looking at one aspect of the project, but not caring about what the entire project is all about. And a lot of things are controlled by government policies and environmental laws, so you need to look at that one. So this is really fascinating in terms of combining all these things. So geoenvironmental or geoenvironmental engineering is application of all relevant multidisciplinary knowledge to understand and develop holistic engineered solution to the geoenvironmental problems. That could be waste management problem, polluted sites, sustainability, geohazards, resiliency, and so forth. So it's like embracing multidisciplinary background to understand the problem first, and then coming up with a solution that is effective, that's sustainable, and that is resilient. So this is a multidisciplinary technical approach. I mean, you can see now many research organizations, funding agencies, they want multidisciplinary research proposals. The days of somebody working in their own field, writing the research proposal, on the area that they want to work on, those are gone. In the US, you have to write a proposal that addresses the unique problem or the real world problems in a unique way. The uniqueness comes from multidisciplinary technical approach. So you can look at this reference for more information on how geoenvironment engineering has evolved. There is a difference between environmental geotechnics and geoenvironment engineering. Environmental geotechnics is application of geotechnical engineering, such as settlement analysis, slope stability analysis, seepage analysis, in addressing the geoenvironmental problems. It's a narrow focus. So with a soil mechanics background, you can contribute to geoenvironmental problems in a narrow way. But geoenvironmental engineering, on the other hand, you need to have a multidisciplinary knowledge to understand and develop engineered solutions to the geoenvironmental problems. It's a broad focus preferred. So the question is, hey, can you have multidisciplinary background by yourself? The answer to that, you need to try to do your best to understand the relevant background or relevant information from other disciplines, and try to work with collaborators and try to address your problem in a multidisciplinary angle. So for these things, of course, soil mechanics and geotechnical engineering is needed. Plus, you need some chemistry, some biology, and maybe other technical areas depending upon the problem that you are dealing with. Some chemistry, some biology is extremely important. Now the question is, in good old days, geotechnical engineers were learning only geotechnical engineers. They are not interested in chemistry and biology. If you ask them to learn something, they would, they would run away. Or they will argue with you why you need all that stuff. So the old days are gone. Now new days where we need to not necessarily the masters of those interdisciplinary subjects, but some relevant background. At least you should be able to know the terminology so that you can communicate with your interdisciplinary collaborators. If you're working with the person from chemistry, or you're working with the person from microbiology, if you are dumb and you don't know any terminology, what are you going to talk to that person, right? So you need to have some basic background so that you can communicate and get their help in advancing the solution to the problem. So I highly recommend you to get hold of this book to get a general overview of geoenvironmental engineering. The first part, basic principles, it just talks about, as I said, basic, starts with the chemistry, geochemistry, groundwater flow, contaminant transport. So those basic stuff, if you're not interested in, taking the courses, but you want to get the relevant initial background, so that first part would be good. And then, contaminated site remediation is one of the major problems in geoenvironmental engineering. Landfills and impoundments is another area of interest, and emerging waste management technology is another area of interest. At least you can, these are very, these chapters are very easy to read. I wrote it such a way that you can easily follow, in a logical sequence. So I highly recommend you to get hold of this book from any library and start reading, any, section that you are interested in. So in terms of the geoenvironmental engineering projects, I wanted to categorize into these 3 types, okay? And it could be done in a different ways, but I try to, kind of make it a simple category. So the first category is safe disposal of non-hazardous and hazardous waste. So obviously, you need a circular economy where you don't create the waste at all, but it's far from the reality. No matter what you do, you're going to generate some waste. So how do we handle that waste? And if you don't handle the waste properly, you're going to create all kinds of problems. So realizing the fact that, our ultimate goal is to have that circular economy, but still you're going to have waste. So how do we do that? One way is to design containment systems, landfills and impoundments. That involves a lot of soil mechanics and geotechnical engineering. Basically you need to have liner systems. They are made of compacted clays, hydraulic conductivity, and that controls the seepage. But you have to also look at the pollution transport. So that's where you need to get the chemistry background. You should know the diffusion, you need to know advection, sorption, some reactions if that could happen. So that's where, as I said, in addition to geotechnical engineering, you need other background. So that's one category of the problems. If you are new researcher or new faculty, you can consider this as one area and then see what are the opportunities to do research. Waste means, there are all kinds of different ways that you can work on. Then a second category of the problems in geoenvironmental is characterization and remediation of polluted sites. So you have a lot of polluted sites. I mean, in US, we take this problem very serious. We have environmental laws and regulations. Every industry, every polluter has to follow. If they don't follow, they will be penalized and they may even go to jail. So it's a very strict law enforcement. In India also, I understand you have laws, but there are a lot of contaminated sites. They are not addressed. You have a dump sites, and and contaminated sites, you don't even see them. Dump sites, of course, you can see the dump sites openly, but polluted sites you won't see it. Those are hidden underground. So for this one, site investigations is important. How soil is contaminated, groundwater is contaminated, how much is contaminated. So all the geotechnical investigations that you do the same thing. One additional thing that you have to do is, in addition to characterizing the soils and rocks, groundwater, you need to also know, the contamination. So for that one, you need to collect the samples, do the chemical analysis, or you can have in situ probes like, CPT, right? In geotech, you use the CPT, cone penetration test. And then to that, you put a sensor, and then, as you drive through it, you get the geotechnical parameters. You also get some signature that can indicate the contamination issues. In situ, a lot of geotechnical work. The slurry walls, grout curtains, cap. These are the things that we use, in geotechnical engineering. But in addition to hydraulic aspects, we need to look at some chemical aspects. So that's where the chemistry and biology is needed. And then you have a soil and groundwater is polluted, and that needs to be remediated. There are different technologies for that one. I know in India, there are severely contaminated site. Green Tribunal, I understand, has ordered them to be cleaned, and it has to be done. And idea is you need to have you need to know what are the different technologies are available, which one is the best suited for addressing that particular problem. The last category of problems are kind of a very general enhance environmental sustainability and resiliency. It's kind of a beneficial use of waste materials, using the dump sites, using those sites for some beneficial use, carbon sequestration, because decarbonization is extremely important from climate change point of view. Renewable geoenergy is important from, again, fossil fuels are contributing to a lot of greenhouse gas emissions. So if you can go to renewable energy, geothermal, a lot of geotechs are working on geothermal, landfill gas, biomass, all those things could be explored. So when somebody says renewable geoenergy, it's not a geotech topic, but you can find geotech and geoenvironmental aspects in any project that you can think of. And the last one is nature-based geoengineering, like phytoremediation, bioremediation, biocementation, all using the nature-based solutions to address the problems, even as the geohazards, like biocementation or MICP for liquefaction resistance. So these are the three categories of the problems, so you can find it. So what I'm going to do is, during the 5 days, every day I want to focus on some of the projects. So what I was thinking is to present 2 of my research projects related to environmental remediation, and 2 of the projects related to waste management and landfill engineering, maybe 1 lecture on life cycle assessment and sustainable resilient engineering. So, but give me feedback on any topics that needs to be addressed. I will be very happy to talk about the one which you are interested in. Okay, my idea is to cover typical environmental remediation projects, typical landfill engineering projects, and typical sustainability projects. So that should give you an idea about how the research could be done, and you can pursue. Hopefully, it will help you pursue your research. So the first one, I said from the first category, environmental remediation, I will, I want to cover like 2 research projects that I worked on over the years. The first one is electrokinetic remediation technology. I don't know how many of you are familiar with it, but first of all, I want to talk about the problem of contaminated sites, and then one of the technologies is electrokinetic remediation technology, how it could be addressed. Before I get into this, I want to see if any of you have any questions on what I talked about so far. Let me see the chat box if anybody has any questions. General topic. Anybody has any questions on what I covered about geoenvironmental engineering and general projects in geoenvironmental engineering? Let me pause for a couple of minutes here. So I will give you a chance to type your questions in the chat box. Anyone has any questions? All right. So I don't want to go too fast without taking the feedback. If you don't have any questions, that's fine. But as we go along, please type your questions, and then I'll be able to answer those questions. So what I want to do is I want to share one of our projects that's about electrokinetic remediation. So before that, I want to talk about the issue of contaminated sites. So I would like to talk about the problem of contaminated sites. What are the remediation technologies that are there? One of them is electrokinetics, what it is, what are the fundamentals involved in it, and what research that we have been doing at UIC on this topic, and what are the practical issues and considerations. You do the research and then you want to take it out to the field, then that's when you have to address all these practical issues. And then I will make some closing comments on it. So now the problem of contaminated sites. So if you're, a new researcher in India, I don't see too many people working on these contaminated sites. It's a great opportunity to, develop your expertise. As I said, you can look at the pollution control board, right? You have Central Pollution Control Board. You go to that website. There's a website about contaminated sites, and they listed many contaminated sites in India that needs to be cleaned up. So it's the real problem. Problem is actually identified. Even look at the Green Tribunal. Orders to clean up heavily polluted sites. I highly recommend you to look at that one and see if anything is happening at those sites. To my knowledge, there needs to be a lot of expertise to address these issues in India. So there are thousands of contaminated sites. As I said, these problems are not visible because if the contamination went into the ground, the soil is contaminated, groundwater is contaminated. But at one site in India, I know people get the water from their wells, and the color of the water is yellow. Obviously, the chemical analysis was done. It's all chromium, excellent chromium, toxic excellent chromium. So obviously, you don't need any other investigation, but to conclude that there is a groundwater contaminated that needs to be cleaned up. You cannot drink or use groundwater that is contaminated with excellent chromium. But in many places you may not see the color, you may not see, you cannot smell it. So, but it could be posing huge problem to the people around that area. So in the US, we have a better control on contaminated sites. We have a good analysis of the contaminated sites and what are the different types of sites that we have, and estimated cost to clean up those sites. Contaminated sites exist all over the world, European Union and other developing countries, Brazil, China, India. As I said, this problem is now, being addressed by all these different countries. So there are many sources of contamination of soil and groundwater. I listed some sources here. For example, air pollution, right? In the air, you have a lot of particulate matter. What happens to that one? Ultimately, that falls onto the ground and mixes up with the soil, and the soil is contaminated by the air pollution. And then infiltration of contaminated surface water. The water, could be storm water that is passing through the streets, or it could be land disposal of solid and liquid waste. Some companies right now, you need to look at how they are disposing of their solid waste and liquid waste, and are they just dumping in their backyard, and thinking that putting into the ground is the easy way, cheap way to get rid of their liquid waste, but that is contaminating the soil and groundwater. And again, it does not stay at the same place, right? Where you dump it. You have hydraulics and other transport processes that will cause the contamination to spread. If you think that there is a chemical company, few kilometers from your house, you think your house is safe? No, there could be a groundwater plume emanating from that contaminated site, from that chemical plant, and it may be spreading underneath your house, or the plume may be migrating through under your house. So that cannot be assumed. So accidental spills are very common. And then you use a lot of fertilizers and pesticides for agricultural purposes. Excess amounts come in the runoff, and that will contaminate the surrounding water bodies, soils. So waste dumps, of course, mining is another area where a lot of contamination occurs because any mined substances you need to characterize if they have any kind of a toxic contaminants. They could be spread into the environment. So if you ask what would be the main source of contamination, so land disposal of solid and liquid waste would be the main source of contamination. So this is where you don't have engineered landfills or impoundments, and you are disposing it off, and then obviously that is entering into the subsurface, contaminating the soil and groundwater. Now, as I said, if you dump something into the ground, what is the problem, right? So this is the problem. So if you have a contamination, you could have a direct exposure to the contamination. If it is near the surface, you could be causing the ecotoxicity to the birds, plants around that area. And if groundwater is contaminated, and if it is generating the plumes, there could be a vapor intrusion, and the groundwater could be contaminated, and you may be drinking the groundwater, and groundwater that is contaminated is getting into the streams. So all these problems, eventually, you are exposing the public or to the surrounding environment, and that's not good. Why that is not good? Because these chemicals, we call those contaminants, those are nothing but chemicals that you learn in chemistry subjects. In the chemistry subject, they never call these as contaminants, right? There are chemicals, and the chemicals are needed for different purposes. That's quite sure, right? But these chemicals are in the wrong place, doing the wrong thing. So that's why we call them contaminants. And all of these contaminants, you can characterize the contaminants into inorganic contaminants, organic contaminants. You need to make sure that you don't have any of these things in your. Sometimes you have excess pH, excess nutrients, excess microbes could be also a problem. So these are all bad because they cause adverse effects on humans, especially the cancer. And of course, you have a non-cancer diseases. And then they are also affecting the ecosystem. So that's why, these are not acceptable, right? So we need to do something about it. So what can we do something about it, right? So what we have to do, okay? Let's say you have a contaminated site, and how can I clean up, okay? So what you do is you do the site characterization. Like, if you have a geotechnical project, what do you do? First thing, you go to the site and drill the boreholes, collect the soils, rock samples, and look at the groundwater level and all those things, right? So that's what you do it. But in addition to that, you need to look at, contamination, type of contamination and their concentrations. So that's called site characterization. Then you ask, based on the results, you say, is the site contaminated? You say no, then you don't have any issue. That site is clean and you can do whatever you want. If the site is contaminated, in the past, the next step would have been remediation. Oh, let's clean up, But this new task was introduced some years ago. That's called risk assessment. So what we have to do is, you have a contamination. Is it posing any problems? Let's say, your contaminated site is somewhere in remote area. There is nothing around, humans are not affected. Ecology is not affected. There is no risk, right? If there is no risk, then you don't have to worry about, cleaning it up. But if it is in an urban environment and people are, drinking water, retrieved from the groundwater, and a lot of people are consuming that, then it could have health effects. If you have health effects, then you need to figure it out how much is acceptable. All our bodies can take, some amount of chemicals without any, health impacts, except, carcinogens. Even little bit is also bad. So you calculate the risk, right? Here, there's a quantitative methodology by which you can calculate the risk in a quantitative terms. For non-carcinogens, it's called hazard index. For carcinogens, carcinogenic chemicals, we call it, carcinic risk. So you have those values, and based on that, you see, whether it's contaminated or not. If the risk is more than acceptable, then you need to go about remediation. If it is less than acceptable risk, then you don't have to worry about it. Now, the question is, it's impossible to take out all the chemicals from all the contaminants from the soil and groundwater. That was not realized in long time ago when, people started to clean up the soils and groundwater. They thought, they can clean up to the pristine conditions, the conditions that were existing before the contamination occurred. From water, you can take it out. From the water, from the air, you can take out all the chemicals that you want. But once it goes into the soil or groundwater, it's impossible. You don't have any control on it, right? In the water, if you have water, you can put it in a batch reactors and do something with that one. You can control the pH, you can control the temperature. But in the soil is so heterogeneous, and it has so many, inorganics and organics, organic matter, and the binding of these chemicals could be so strong into the soil. So you cannot really take out the contamination completely. So you can leave some contamination and not have the risk. So that's based on that. You have to look at what are the concentrations that can be there that provides the risk less than acceptable. So those concentration levels would serve as your remedial goals. So I have contamination, so much, but I need to reduce to these risk-based levels. So that is our target. And how do you accomplish that one? So that's where you need the remediation technologies. How do I reduce the concentration from this high risk level to the non-risk level? Not zero, but non-risk levels. So here you could have multiple remediation technologies, and you have to choose the best one. In order to do that one, you should know what are all the different remediation technologies are out there, right? Unless you know different technologies, at least in a preliminary way, then you can rule out some technologies that don't work, and you can concentrate on the technologies that would be feasible. And then, your goal is now to see which one among those could work to be chosen, right? And then once you choose that one, and then you design it and implement it, and then during the implementation, you monitor it. Are the concentrations decreasing with the progress of remediation? If it is happening, and if you get finally the results as you targeted, then that will become the useful site. So this is a systematic approach that we follow. I mean, sounds easy, but in reality, this could take months and months and a lot of money to be spent doing these things. So this you have to keep in mind, where the remediation technologies are coming. You need to have a site characterization done, risk has to be calculated, and then risk-based levels have to be defined, and then choose the technology that works. So site characterization, risk assessment, those are the major tasks, and the remedial goals and remedial methods, alternatives comes later. So this is where you need to have a remediation technologies background. Now, if you have one remediation technology, is not going to be applicable everywhere and solve the problem. So I like this schematic, one is the source containment. Let's say you have a dump site, and underneath the dump, you have a soil and groundwater is contaminated. How can you clean it up? It's a large area, deeper level of contamination, just, trying to clean up the soil and groundwater at that site is, enormous task. So instead of, addressing the soil contamination, groundwater contamination, what we do is we put a containment around it. It's called slurry walls, right? or vertical barriers. We can put that one and then key into the clay layer and basically make sure that the contamination does not spread more than the area that is there, that is existing right now. That's the most economic option and more environmental friendly option. So you need to keep in mind that vertical barriers are going to be the important remedial option in contaminated sites, especially like a large dump sites. Then you have a soil and source zone remediation. Number 2 is here. If the contamination has happened here, okay, in the VADA zone, before it does not reach the groundwater, but it is in the VADA zone, in the unsaturated zone, and there's a lot of concentration here, right? If you have it spilled right in there, that area, they have a lot of concentration. So we call it source zone because that's like a source that will cause the groundwater contamination. So you need to clean up that contamination. So again, you're talking about the technologies that can work in unsaturated zone, and contaminant concentrations are higher. That's only in the soil. Now, if the contamination, you didn't address it, but the contamination infiltrated into the groundwater and it formed a plume, and then you have high concentration plume here, high concentration plume, right, initially. And then what kind of technology that you can apply to reduce these concentrations? That's a huge problem, right? So you have to have different types of technology with high concentrations. Now, let's say, you ignored this problem for many years. This plume has spread, large area. And if you look at the areas, larger areas, distance far away from the source zone, the concentrations may be very, very low, but, low concentrations, but large area. Think about it. You cannot apply the same technologies that you have used in this groundwater source zone to this large area with low concentration. So you need to have a different thinking about that one. That's called groundwater plume remediation. So this understanding has to be very clear. If you have a contaminated site, you need to understand the site and the contamination and how it is existing. And then you have a suite of technologies that can be used to address the situation that you have. So you cannot be expert in one, you can have expertise in one particular technology, but you need to have a good idea about what are the other technologies that can go with it to solve the problem. Okay. So here are the, from the book, remediation methods, the monitored natural attenuation is one of the options. So one option is, do you have naturally occurring bacteria, microbes in the ground, in the soil or groundwater? Is it naturally, contamination is naturally degrading, right? And so you could do some, during the characterization stage, you can collect the information to see if that is happening. If that is happening, you don't have to intervene and make that natural. So, nature-based solutions that we're talking about is like, we're not doing anything. Naturally, there are microbes that are present in the soil or groundwater. You let it, happen, but you need to monitor, make sure that contamination concentrations are decreasing. Generally, this natural attenuation is very slow. So you really need to create the conditions for the microbes to be very active and abundant. That's where you create an engineered system to enhance the attenuation, natural attenuation. Those are basically, we're talking about bioremediation, phytoremediation, those kind of things, or introducing the nutrients. So then you have a containment technologies here, ex situ containment, in situ containment, the landfills and impoundments. And then, in situ containment, this is you have a passive systems, horizontal barriers, vertical barriers, and caps. And you have active systems, pumping and subsurface drains for groundwater. It might look overwhelming, but it's very important to have an idea about all these things. As I mentioned, if you look at that book, it will give you very good idea about all these things. So you need to at least know what these are, right? And a lot of opportunities to do research in many of these remediation methods. In situ soil remediation methods means, you don't want to dig out the soil. You want to treat it right where it is. That's called in situ, right? So your technology could be physical, chemical based, or thermal based, or biological based. So depending upon what process that you're using, you could have a different technology. So the physical chemical is these are the technologies: soil vapor extraction, SS technology, solidification, stabilization technologies, chemical oxidation reduction, soil flushing. Electrokinetics is one of these technologies. Thermal, basically you're heating up the soil. Low temperature is soil heating, and very high temperature is remediation. Then on the biological methods, you have bioremediation, bioventing, phytoremediation. So these are the methods in situ. You don't have to dig out the soil. You can clean up the soil right where it is. So this is kind of a preferable because you have less disturbance to the site, and site can be in operation. But if that is not possible, if it is easier to dig it out and treat it on site or off site, okay, excavate that one and have a treatment plant right at the site and do the treatment, or you transport to a treatment facility and treat it there. So again, these kind of technologies can be used in that case: solidification, stabilization, bioremediation, thermal desorption, chemical oxidation reduction, soil washing. Electrokinetics is one of the technologies. Incineration is another technology. On the groundwater side, again, there are different technologies. So ideally, you pump and treat is not, you're pumping it out and treating above ground. But other technologies like air sponging, permeable reactive barriers, flushing, chemical oxidation reduction, chemical immobilization, electrokinetics, bioremediation, phytoremediation. These are all, done on the groundwater without extracting any groundwater to the surface. So you need to have a good idea about all these things. Again, these are all like, based on the conventional geotechnics, plus having additional chemistry and biology backgrounds. So as I said, use this book to learn about these things. I highly recommend to get hold of this book so that you will have a good understanding of what are all these different technologies are. All right. So any questions on this one? You can unmute and ask me a question if you want.
So the workshop has been designed to have a more interactive session. So that's why sir is asking, in between. So please make sure that, you will interact. And the lectures are also available on recorded later, but it is always good to interact. So I request all the student participants especially to kindly interact.
Yeah, don't be shy. Just ask any question that you have. So I'll be happy to answer. All right, question is about, can you explain about soil heat vitrification? So, there is thermal heating. You heat it up. As you heat it up, then you have volatile organic compounds come out as a gaseous phase, and then you collect them. And then you keep increasing the temperature, different contaminants vaporize at different temperatures. So you will see, easily volatile compounds will come out first, and the semi-volatiles come at higher temperatures. And then you talk about incineration, right? Incineration is at high temperature where you combust some of the contaminants. And then even you can go into very, very high temperatures, it's more than 1,000 degrees centigrade temperature. That's where you will, melt the soil, and then you cool it. It becomes like a glassy structure. So that's called vitrification. So vitrification is, converting your soil into a glassy structure. So basically you are destroying the soil. Then, you say, who wants that kind of technology? So you heat up the soil and cool it, and it becomes the glassy structure. That technology is used by Department of Energy, where they had radionuclides, they had metals, they had organics, all kinds of mixed contaminants that you have, and there's no technology that can really address the problem. And if it is posing risk due to the release of those contamination to the surrounding environment, what do you do? So basically you heat it up and convert into like this glassy vitrified material. So all the contamination is going to be trapped in that glassy structure. So it's like a stabilization certification. It's like adding let's say you add cement and contamination gets bonded to the solids and it may not leach, right? But whereas in case of vitrification, so you're converting in a physical form into glass structure, and then that's going to trap all the contaminants. So you don't have any other option other than doing this. So that's so heavy metals which are present in leachate at landfills. Listen, that heavy metal leachate quality is going to change depending upon what kind of waste that is disposed in a landfill or dump site, right? And also it could change with the time. So you could find the literature on the typical concentrations of different contaminants in leachate. Even in my book, I have like several pages of one table that continues into several pages, different chemicals, and I've given you the range of concentrations. The range could be varying, parts per billion to, thousands of parts per million. Okay, so don't ever generalize the leachate concentration. So only way to find out the leachate concentration is to go to the site and collect the sample and analyze it. And then again, as I said, it varies from time to time because, if you have a degradable fraction in the waste, as that degrades, then, organics could change. And then the metals that are absorbed onto organic matter now disappear. So they get into the solution. So you really need to look at that one. So how the metal contamination or leachate affects the soil properties, it depends upon the soil you are looking at it. And then looking at leachate composition. So some, in the soil you have minerals, you could have, oxides and hydroxides and organic matter. So that's where, understanding the geochemistry becomes important. Again, you cannot really generalize because the soil at each site could be different and the leachate composition could be different. So if you are interested in, addressing a solution to a specific problem, I will suggest you to go to that site and collect the leachate, collect the soil, and do the testing. But if you are generally interested in science aspect of it, then you consider an ideal soil and ideal metal conditions or contamination conditions, and then you simulate that testing in the lab and look at that one. So what about tell the advantages of electrokinetics, then stabilization. So I will talk about electrokinetics soon. You will be able to answer. Any database available regarding hyperaccumulator? Yeah, I mean, when you're dealing with phytoremediation, you really need help of ecologists. Okay, so even though I tried to learn as much as I could, but it's impossible to learn this ecology, the plant species, and there's a lot of information about it, which plants will survive under which soil conditions, pH conditions, and their characteristics of uptake of the contamination. But I would not generalize it. I mean, you can find the typical plant species that can work in different conditions, but doesn't mean that that plant is usable at the site that you are interested in working, because a lot of invasive species are not allowed. Again, our experience was that we did lab research on certain plants. We found out that contamination could be uptaken by these plants very well, but then when we wanted to use it in the field, the environmentalists said no, we cannot use those plants at the site because we're going to damage the ecology. So we need to use the plants only native to that site. So you really need to, a lot of things go into that. Explain about carbon sequestration using biochar I will be presenting that one later on. You will see in the landfills, as the landfill gases come up, you can use the biochar to sequester the carbon. I will talk about that one in my future lectures. I'm happy you guys are now, loosened up a little bit, asking questions, which is good. I'm going to save all the comments that you provide, and I'm sure I will have your email address from your registrations. I will be happy to, respond to those questions. So keep typing the questions. I want to see that the chat box to be very busy. Okay. More about pollutant soil vapor and its remedies. Yeah, I think, as I said, having the knowledge about different remediation technologies is very important. So soil vapor extraction system is one of them that can be used to remove volatile organic compounds from the weather zone. And then if you want to take out the contamination from the groundwater, this is called air sponging technology. That's why, the best thing is to, not necessarily my book, that my book is really good to get that good idea about. What I did is, what is the technology, where is it applicable, what are the advantages, what are the disadvantages. For each technology, you have that information right up front. And then I have, one or two case studies where the technology has been used. So I think that should give you a really good idea about, just some information about what the technology can do it, where it is applicable. I would suggest you to look at that option. And if you have any questions, let me know. Okay, let me just thanks again. I will give you an opportunity to comment as we go into the future, as I continue my lecture. So we talked about this one. Now, no matter which technology you're talking about, we have really some challenges. The challenges are these. If you have a clay soils, they are damn difficult to clean up compared to sandy soils because of their low permeability and complex composition, right? Let's say if I'm trying to flush something into the soil, how can I flush it if I have clay soil? If I have a sandy soil, I can, introduce whatever reactive agents that I want, right? So the clay soils are very difficult. Other things, if you have a geotechnical background, the subsurface is not beautiful, homogeneous soil conditions. You don't have a sand, existing, or you have a clay existing. You have, these layers, lenses. You will have a complicated subsurface condition. No matter where you are talking about, most of the times you're going to see the heterogeneities. And then how can you, do the cleanup when you have these heterogeneous conditions? So let's say you are trying to flush something or introduce something into the ground that is going to flush through only the permeable zones, permeable soils. And you have a clay lenses, it's not going to go through the clay lenses. That's a big problem. Then if you have organic contaminants that are hydrophobic, right? So they don't dissolve in the water. Let's say I'm trying to pump out the groundwater that is contaminated with hydrophobic organic compounds. These hydrophobic organic compounds are not going to be dissolved in the water. So you're never going to get it out. So that's, there are a lot of places you have these kind of contaminants. And then heavy metals. You have very few technologies to clean up heavy metals. Organic compounds, there are many different remediation technologies. For example, bioremediation works for only organics. And some soil vapor extraction, for example, it works only for organics. So very few technologies are available for heavy metals. And then moreover, if you go to any site, you don't have one particular type of contamination or one category of contamination. You will have mixed contaminations. You could have metals, a bunch of different types of metals, okay? And then you could have, organics and metals together. So at every site, depending upon what happened at the site. For example, if you go to dump site, you collect the groundwater from that site, you probably find everything, right? So how do I clean it up? These are the challenges, right? So if you have these kind of problems, this in situ electrokinetic or electrochemical remediation has the potential to address this. Now let's see how it can be done. Okay. First of all, what is electrokinetic remediation? So what electrokinetic remediation is like this. Let's say you have a contaminated site, right? So what do I do is I put a well on both sides, or I could have wells, within the contaminated zone. Then I will have electrodes in them, and then I apply small electric DC power to that, right? So the positive is anode, negative is cathode. So I apply the power. Then as soon as I apply the power, then you will induce these kinetic processes. So once you apply electric potential, these positives want to move towards a negative electrode, and negatives wants to move towards the positive anode if they are in a dissolved phase, right? And some contaminants could be in a colloidal phase, right? So depending upon the overall charge of those, they could move towards the anode or cathode. So that process is called electromigration. Electromigration is movement of cations or anions or charged colloids. So that happens, right? The electromigration, these colloidal particles, that's often called electrophoresis. Electrophoresis mostly, those colloids, and then ions are, electromigration. Then in addition to that, if you are dealing with clays, you have a double layer effect, right? Your surfaces are negatively charged, and you have a double layer, and then you're going to induce the flow because of this applied electric potential. So you have electromigration, electrophoresis, and electroosmosis generally happens from anode towards the cathode, but that not necessarily always true. It could happen, reverse way also. So there are a lot of research that has been done on these different processes. So what happens is because of these processes, the contamination, you are targeting the contamination to move from contaminated soil zone into the electrodes, either towards the anode or cathode. And then once it comes into this well, you pump it out. But the problem is, the contamination has to be in the solubilized form for the contamination to migrate towards the anode and cathode. Let's say you have hydrophobic contamination. That's not, solubilizing. So you need to introduce something that can solubilize. So that's where this is called conditioning solution. So anode conditioning and cathode conditioning. So you want to introduce the solution into this electrode, anode, and then when you apply electric potential, that is going to be transported into the soil. As it transports, contamination is going to be solubilized, and then these other processes, electromigration, electroosmosis, and electrophoresis will remove that contamination. So the idea of this conditioning solution is to introduce that solution into the soil so that the contamination gets solubilized. Okay, and once solubilizes, then you can get these processes acted on that, and then you get the removal. So when the contamination comes into the electrode well, you can pump it out, and then you, depending upon what contamination is coming out, you can treat it. It could be, carbon filtration or, precipitation or whatever wastewater treatment technology that you can use it. And then, you can recycle that conditioning solution. The conditioning solution could be like a, surfactant. It's like a soap. Okay, that's very good for organics. Or if I have inorganics like metals, I could use a slight acidic solution, reduce the pH, then the contamination could be in the soluble form. So you really need to match the conditioning solution to the chemistry that you want to achieve. So there's nothing you have to do. Just put the wells, put the electrodes, and apply low DC supply. You're not talking about consuming a lot of power here. And then you have to adjust the chemistry based on the conditions that happens. So this is the, in situ. Ex situ also you can do it. You can create these reactors. You could have, electrode chambers, and then you put the material in there, and then you introduce the solutions if you want it, and then you treat it. So same processes, Instead of underground, you can just create this one in a reactor above ground. So for example, we used for a sludge treatment. So you put the sludge in the middle, and then you put the electrode here, and you purge the solution, whatever you want to solubilize the contamination. Contamination comes out, and then you can take out the liquids, and then you pass through the carbon filter, or in this case we use that one, but we'll find a way to take out the contamination that comes in the water. So the sludge as a contamination, and it's hard to get that contamination out of the sludge by applying electric potential and using appropriate conditioning solutions. You are trying to move the contamination, remove the contamination from sludge and transport that one into the electrodes, and then you're pumping that one out and then cleaning that pumped out water. So there's a lot of advantages. What is this? It's a simple equipment. We're talking about simple equipment to use and easy to operate, right? And relatively inexpensive. This is a question mark depending upon what electrode you're using, what is the electrode spacing, all kinds of things like that. And relatively safe, again, you're not using AC power supply, high, voltage or current level, so it's safe. And it can be done in situ or ex situ, as I showed you. And you can apply for soil or groundwater, and it can be applied for different types of soil. So that electroosmotic flow and electromigration, those processes are less. Electroosmosis is mostly for clays, but these other processes, electromigration, electrophoresis, will happen no matter what type of soil you're dealing with. You can apply to low permeability soils, unsaturated soils, unsaturated soils, heterogeneous soils. So as I said, once you apply electric potential, the direction of those ions moving, does not matter, whether it's passing through the clay or passing through the soil, as long as the pore water is connected. So it's transported to the pore water, and is applicable to a variety of contaminants. So it could be metals, radionuclides, organics, in individual forms, or you have a combination of these things. So the metals and organics, metals and radionuclides, metals and or just a combination of the metals. So which is, you can have a mixed contaminants. So it can be also easily integrated with other technologies. So I don't think there's any other technology that is so flexible, has so many advantages as this electrokinetic remediation. So that has been main attraction for me to work on this technology, right? So again, subsurface, is a challenging to deal with variable subsurface conditions from geotechnical point of view. And then if you have a variety of contaminants from chemistry point of view, that's complicated. So combining this geotechniques and environmental aspects together, this can be accomplished by this electrokinetics. So as I said, electromigration is the one process that is dealing with the ions and ion complexes. Electroosmosis is the bulk movement of the pore fluid through electric double layer in clay soils. Generally, as I said, occurring from anode to cathode, but it could change. Electrophoresis is transport of charged colloids. So these are the processes that move the contamination out of the soil into the electrode, right? There's other thing that happens when you apply electric potential. So here is the electrode, right? Is at the anode you have a cathode. Once you apply power supply, then electrolysis reactions will happen. So water will, you will have these reactions. So at the anode, water is going to dissociate, and you have H+ ions, and then oxygen is going to be released. At the cathode, you have OH- ions are going to be created, and H2 gas is going to be generated. Generally, we let oxygen and H2S emitted into the atmosphere. Sometimes, there's some people are trying to trap this one and use it for beneficial purpose also. But, they say you can emit into the atmosphere. That's okay. They are not toxic. So H+ ions that you have here, what happens? It tries to move towards the negative. That OH- ions that are generated here, they try to move towards the anode. What is the H+ and OH- does? That is H+, and basically the concentration of H+ is pH, right? The pH reflects that one. So pH is going to be reduced as H+ ions going to go into the going to the soil due to electromigration. OH minus ions, as they enter from this end, the pH is going to increase. So you have, let's say you have some soil pH, right? Start with, and then you will see that soil in this area is going to be acidified, and this side is going to be alkaline. So this, you basically create an acid frontier, and you create an alkaline frontier. So based on the treatment process, the length of the duration, so this acid front is keep going this way from anode to cathode. This alkaline front is moves from the anode, from the cathode to the anode. So you will see the shift in pH change. Okay, I will show you some results of that one. And that damn thing is going to complicate the whole chemistry in this process. So pH changes spatially, okay, changing from location to location, and it changes temporally because, you know, this acid is migrating, you know, with time. So the spatial variation and temporal variation, with the distance and with the time, they are changing. So that complicates this technology. As the pH changes, you're going to have these geochemical processes are going to be affected. Absorption, desorption, right? Contamination, you know, is it in the pore water or is it attached to the solids, right? We want in the pore water, but it will, you know, the contamination can be in the pore water at certain pH. If you are decreasing the pH too much, is not good. If you're increasing the pH too much for some contaminants, it's not good. So you're complicating it. You know, that absorption, desorption is extremely important. So the soil type and, you know, contamination type that you're dealing with and the soil composition, that makes a lot of sense. Precipitation and dissolution. This is also a very important process to look at it. Is the contamination getting precipitated or is it solubilizing and getting into the water? And then we could have oxidation reduction, speciation change. You know, you could have a chromium in, let's say, a trivalent chromium form or hexavalent chromium form. And the way it transports is totally different. I'll show you an example of that. So you could have a speciation change. So those are the things that we need to understand. Generally what happens is contaminants are desorbed or solubilized in the soil, right? And then you have H plus or OH minus or ions are formed electrolysis due to electrolysis of water. The H plus transports causes the desorption and solubilization of cationic metals, but hydroxide transport causes the desorption of anionic metals. Contaminants are migrated towards the electrode. Electromigration of anions will happen to the anode. Electromigration of cations happens to the cathode. And then you have electroosmotic flow, and you have advection that is caused by that goes towards in the direction of the flow. So generally anode to the cathode. The ions and organics, since they don't have charge, so you won't have electromigration or electrophoresis. So only thing that you have to rely is on electroosmotic flow. So organics not having charge, they will be flushed by electroosmotic flow from anode to the cathode. So ions are going to be, again, depending upon, let's say if you have a cationic ions and they are moving towards the anode, your flow is in the opposite direction. So you have to overcome that electroosmotic advection, again is the electromigration. So, and contaminants are captured in the electrolysis. This is kind of how the basic thing, you know, happens. And then once the contamination comes out into the solution, you pump it out and treat it and recycle the pumping solution. So the whole fundamentals of electrokinetic remediation, very fascinating. You have electrolysis reactions that are happening at the electrodes. And then you have a transport processes happening, electroosmosis, electromigration, electrophoresis, diffusion happening. And all those are going to be affecting the sorption, precipitation, oxidation, reduction, complexation. So basically you have a dynamic geochemistry that varies spatially and temporally. And it changing the solution chemistry and also solid properties, solid surface properties. So if you want to look at, you know, very complicated problem, this would be the best problem to look at it. And it's fascinating, you know, if you really want to get involved more into science, and this would be the opportunity to do that. So you can find all this, you know, the background information about electrokinetics from this book. We wrote several years ago. It's an edited book, and we summarized all the work that is done in this by that time. So it's a good starter. I want to explain how we did some studies, okay, in our lab. Our research is, our research premises is, if you can understand, control the geochemistry, you can accomplish whatever you want. Okay, so you have to understand the geochemistry, and then you can engineer the geochemistry to accomplish whatever you want. So the fundamental premise is to understand the geochemistry, and then if you understand the geochemistry, you can engineer the geochemistry to favor what you want. Otherwise, if you just try and error, it's not going to happen. Nothing, you will be wasting a lot of your time. So to understand the geochemistry and to demonstrate that you can engineer the geochemistry to favor what you want, we basically run this small column experiments. So these are like horizontal cells. So you put a contaminated soil here, and then you have an electrode on one end, other electrode on the other end. You have a gas vent that takes away the gas. You need to have a way to release the gas, and then you can put a conditioning solution. So it's kind of a simple way of simulating that well system in the field. We're not exactly doing that, but in terms of the principles, it would be the same. And you apply small electric potential. You can measure the current and voltage during the using the multimeter. So you can put the contaminated soil here, and then you can have water going through it. As I said, water is not going to solubilize some contaminants, so you need to put some other solution based on the chemistry that you want. So this is what happens. So once you apply electric potential, all those processes will come into action, and then contamination will move towards the anode or cathode. And our idea is we want to get the contamination out into these end chambers so that we can take it out and treat it. This is the close-up view of the cell. So it's a 19.1 centimeters, 6.2 centimeters. There's no magic rationale for these numbers, as long as you make it workable. And this is a close-up view of, you have a porous stone, you have a graphite electrode, and then you put a filter paper. So these arrangements you can see in details. You can fabricate these cells if you want, yourself in the lab. So this is how the typical setup looks like. This is the cell that we have, the small cell here. The soil here is, you can see based on the color, it's a kaolinite. We always do some testing with the ideal clays, because once you get the field soil, everything is complicated. You don't know the mineralogy of it exactly. So then you see that there's a gas vents here, and then these are connected here. Electrodes, they're connected to the power supply. So and then what you are injecting into it, depending upon the situation. And if you want to collect the outflow, you can collect it one end or other end. So we did the testing on different types of soils to demonstrate the geochemistry effect. We tested kaolin, glacial till, and the sand. So kaolin is the ideal, clay. It has a low permeability 10 to the power -8 centimeter per second. pH is about 4.9. The glacial till is the field soil. And then, hydraulic conductivity is also low, but the pH is 8.2. But in the mineralogy, kaolinite has 100%. Whereas in the glacial till, you look at, if you go and grab a soil out from the field site, okay, and look at the mineralogy of it, it's going to be complicated, right? But it's always good to take an ideal clay mineral and then field soil, do testing simultaneously. What happened is, before I started doing experiments, many people did experiments only on kaolin, and then then they went to the field and they tried to apply and they failed it, right? Because in the field it's not kaolin, it's a glacial till. And my ever since I started doing this research, I have been telling that geochemistry, you need to know the soil composition in order to make this experiment work. If chemists are doing this research, they don't know anything about the soil, right? Only geologists and geotechnical engineers can understand the mineralogy, and that can play a major role in this. Here are some results. It's very interesting. So that column experiments is a small column. So let's say you tested for some time. You looked at what is let's say you collected the solution in the anode, you collected the solution in the cathode, and let's say you section the soil. After you running the test for some time, you extrude a sample and let's say you sectioned it. This is the section 1 near the anode, section 2, section 3, section 4, and section 5, right, is the pH. So initially contamination mass is, distributed evenly, right? And then you see what happens. Section 1, nothing is there. Contamination is nothing there. Section 4, nothing is there. Section 5 has all the contamination. This is the mass fraction. All the contamination that was initially uniformly distributed to that soil sample, now all of that migrated into the section 5 near the cathode. It didn't come into the cathode. Why? Look at the pH profile. In the cathode, you have high pH, the OH minus, and that migrated here. The pH has increased in the section 5. And the OH minus was the H plus ions were generated the anode. The acid front migration is much faster than the alkaline front migration into the soil. So alkaline front migrated only a little bit up to section 5, whereas the acid front migrated all the way to the section 4. So because the pH is lowered here, the nickel we are talking about, the solubility of that one is very high at the low pH. So the nickel was in the solution that was able to migrate. Once it came to section 5, the pH was higher. So look at the pH of this one. And once the pH was higher, that gets precipitated or adsorbed. So it transported throughout the soil and it deposited in the soil itself very close to the cathode. Ideally, we want this one to be in the solution so that we can pump it out. See how it is affecting here? Let's say I took the same kaolin. Now I changed the contamination. Let's say I made it excellent chromium, right? So excellent chromium exists as an anionic complex. So nickel is, right, Ni plus, right, plus 2, right? That's, the positively charged. This one is going to be negatively charged. So look at the same test I've done, except the soil is packed with chromium 6 instead of nickel. So initially concentration is uniform, right? Initial concentration is uniform. Now after doing the testing for some time, look at, pH profile is kind of similar, right? So pH is higher near the cathode and reduced near the anode. Now look at what happened to that chromium 6. At section 5, there's nothing. Section 4, little bit. Section 3, little less. Most of it came into the section 2, section 1, and actually something collected in the anode electrode chamber. What does that mean? Chromium 6, being anionic species, that's going to migrate towards this is the negative charge, is going to migrate towards the anode. So it's migrating. If you have a high pH, the chromium 6 anionic species does not adsorb. So it's in the soluble form, it's coming. When it encounters the low pH, at low pH, chromium 6 is going to adsorb to the soil. And it's retained in the soil near the anode because that has low pH. And part of it came out, but part of it is here. What are we learning from here? Same soil, kaolin, exactly the same soil. I had a nickel here. And nickel was able to migrate towards the cathode, but most of it got precipitated, in the section 5 near the cathode. If you have a chromium 6, that is migrated towards the anode, and most of it got adsorbed near the section 1 and section 2 where low pH is. So that's why you need to look at the soil, the chemistry of the contaminants and the effects of pH. Okay, that's interesting. Now let's say I do the same test on glacial tail. So exactly nickel, right? I basically only thing I did it is the kaolin is substituted with the glacial tail. I took the glacial tail, I spiked with the nickel and did the testing. Look at the glacial tail had, in the anode pH gets reduced, the cathode pH gets increased. But look at the pH in the section 1. Section 1 is about 4.5 or 5. It never decreased. Here it decreased to 2. It didn't decrease in the soil at all. It's not less than 6. Why? But it was able to only increase. The reason is this glacial till has high carbonate content. It has a high acid buffering capacity. It didn't exceed the buffering capacity yet. So as a result, the pH was always high. As the pH was high, the nickel did not move at all. It is almost at the same place. Compare this one with this kaolin. Kaolin, it was able to transport, but glacial till, nothing. Now, same story here. So glacial till with chromium 6. Look at what happened here. All the chromium came into anode. Because of the high pH, the chromium 6 exists in a soluble form. All of that easily could transport into the anode and could migrate, could come here. So these experiments show that if you do the test on kaolin, it's not going to be valid for the field situation. If you did the test on nickel, it's not going to be valid for chromium 6. So this really fascinating and emphasizes the need for consideration of the geochemistry. You need to consider the soil composition. You need to consider the contamination condition. So there are a lot of complications. So soil composition effect matters. You have a cationic contaminants. As I explained all these things, anionic metals migrates towards the anode, and the low pH is a problem for that. So can we give up? No, we need to figure it out. Once we know that the chemistry, we know that they are moving to certain area and or not moving at all. Based on that understanding of the geochemistry, what can we do to remove the contamination? Increase the treatment time? That's not going to affect. Increase the electric potential gradient. Okay, let me put like a high voltage gradient, a high current. Maybe that will change it, or maybe the change of mode of application, maybe periodic versus continuous. Or can I use the cation anion exchange grains in the electrode so that I can restrict the movement of H plus and OH minus ions? Or should I circulate the electrolytes and try to balance the pH? We tried all of that. All those things don't work, but the only thing that works is use of enhancement solutions. So basically you have to use the right chemistry by introducing some solutions into the soil, chelating agents or organic acids for metals removal. So if you do that one, so for example, this is the kaolin. It's spiked with chromium, nickel, and cadmium to simulate one of the field sites that was there in Chicago. And we use the water. Look at the removal efficiency, 12. This is a 0. This is 7%. If I use the EDTA, look at the chromium, 83%. This is the 19%. This is 23%. Right? 10% and the 23%. So you looking at all these options. SWEAK is like a sequential extraction, sequential injection, and that gave 68%, 71%, 94%. These resulted in the concentrations in the soil less than the risk-based level. So this is the best approach that you can follow to get the ultimate treatment. But the treatment is different for glacial till. That was for kaolin. For this one, we looked at the EDTA, acetic acid, citric acid, sulfuric acid. But the SWEAK is the like an alternative sequential electrokinetic enhancement, and that gives you the results that you're looking for, right? So what I'm trying to say is, okay, I want to get some remediation, and it can be done if you can understand the geochemistry. Now, organic contaminants are different. Organic contaminants, whatever works for metals does not work for organic contamination. So you need to use a different solubilizing agents, surfactants, co-solvents, cyclodioxins. So again, these organic contaminations are not in ionic form. So only mechanism that you are relying is on electroosmotic flow. And the electroosmotic flow, it decreases during the remediation process. So in order to increase the electroosmotic flow, what we found is that pH has to be controlled. You need to have a pH more than PGC, point of zero charge. You probably learned in some of your introductory classes, is the pH at which your charge is 0. Net charge on the soil is 0. And then you have to have a magnitude and mode of electric potential application. Basically you have to pulse it on and off. And based on that kind of experiments, we found out that, if you have a continuous flow, continuously, if you apply the electric potential, you will see some electroosmotic flow, it stops. But if you do the periodic electroosmotic flow, periodic electric potential application, you see continuous increase in the electroosmotic flow. This is one of our major conclusions, that if you can apply, intermittent or periodic electric potential application, you can sustain the electroosmotic flow. If you can get this osmotic flow, then your surfactant, whatever you're using, it's going to flush out the contamination. So the main challenge is to maintain that electroosmotic flow. So if you can take out the electroosmotic flow, then you have contamination can decrease quite a, so this is to showing the soil from anode to cathode, what the concentrations are, final concentrations. You see this one with the periodic, is all of them gotten out. Only in the continuous case, you have a lot of that issue. So again, for organics, that would be an option. Now, heterogeneous soil conditions, we did the testing, let's say use the sand. You don't need electrokinetics in sand. So the people, I get crazy when people try to use for sand. Sand, you can flush it hydraulically. No need for electroosmotic, electrokinetic conditions. So, but if you have a clay, you cannot flush it hydraulically. So then you must use the electrokinetics. But here, if you have a layered profile, let's say you have a clay on the top and sand at the bottom, if you try to flush through it, where will the flushing solution go through? It will go to the sand layer. The clay layer will never get cleaned up. But if you apply electric potential, you will generate the substantial flow through the clay also. So you get a good treatment out of that. If you have a clay lens in the sand, if you are trying to flush it, all the water, all the flushing agents are going through the sand. Nothing is going to go through the clay. But if you apply electric potential, you will generate the flow through the clay, and then you get the treatment. So that's why this technology is good for heterogeneous soils. And we have done the tests on mixed contamination soils. If you have organics and metals, both of them can be removed by electrokinetics. But when it comes to the field soils, we collected the soil samples from different sites. So field site A, B, D, E. You look at their classification, and then we try to test them electrokinetically, because you're talking about mixed contaminants here. You have a lot of these metals, right? How can you take those out? We created different test conditions with different conditioning solutions, and then there's a field soil A. You have organic salts. You need to take out the metals and organics from the field soil. And the field soil B is a different story. So every soil, you need to understand the geochemistry first. And if you can understand the geochemistry, what do you want to do it? You want to change the, you have only few controls. One is the electro conditioning solutions. What you want to put it in the anode, what you want to put it in the cathode, and what type of electric potential that you want to apply, what mode you want to apply, continuous or pulsed. So these variables you need to control. And then if you can control them, you can get, So just I want to take a few more minutes to finish up this topic. That's called electrokinetic remediation. Now, you see that when so much effort is needed instead of introducing the conditioning solutions and applying current and all those things. You can get what you want, but it is going to be a little bit more on unsustainable side. Cost may be high, time may be more effort is needed. How can we make this technology a little bit more sustainable? So what you could do is you could use this technology as you can integrate with the other technologies to address their deficiencies. For example, bioremediation. So bioremediation requires probably nutrients. Maybe I can use the electrokinetics as a nutrient delivery system, not sole purpose of removing the contamination. Then you don't have to operate in a intensive manner. So it's a little bit of effort could accomplish the goal that you want. The phytoremediation, the access to the contamination, the availability of the contamination to the plants. So that can be enhanced. Flushing chemical oxidation reduction, permeable reactive barrier, stabilization. These are all like a standard technologies, but they have deficiencies. Can we use electrokinetics as to address those, the deficiencies of those technologies? Because we can, address these definitely by electrokinetics. And the goal is we can detoxify the organics. Okay, if we have organics in the soil, okay, we don't want to remove the organics. Maybe we can use the chemical oxidation technology to detoxify the organics. So we are done with those. We don't have to deal with them in the effluent. Heavy metals, you don't have any choice. You have to recover those metals or stabilize those metals. You can achieve both of them in detoxify the organics and remove the contamination at the same time. The only question is, is it practical? That effort that is required is the practitioners, will they use? Will it be cost effective? Those are the questions that needs to be answered. Is it green or sustainable? But one good thing is, don't worry about the power supply, energy consumption. This is the DC. You can use the solar panels and you get the energy that you want, power you want to run these kind of systems. So just the electrokinetic bioremediation is like, okay, bioremediation is, you want to prefer the bioremediation, but you don't have the nutrients, but we can put these electrodes and then introduce our nutrients into this. Okay, so that becomes electrokinetic bioremediation. Sometimes if you don't have microbes, you can introduce the microbes. Depending upon the charge of the microbes, you can use the electromigration process, or if they're not charged, you can use the electroosmotic processes. So this is how you can address I love bioremediation, but unfortunately I need to deliver the nutrients. And if it happens to be the clayey soils, there is no other way I can do other than electrokinetics. The phytoremediation, right? So if you have plants here, the contamination is away, how do I make that contamination accessible to the plants? So it's an anode and cathode, and you're going to generate the transport of the contamination. And as the contamination comes into the plant zone, the root zone, and they will be uptaken or they will be sequestered depending upon, or degraded depending upon what mechanisms that phyto is based on. So flushing is one thing. Flushing is basically you introduce the reactive solutions here and you pump it out, right? So you put a solution here and you pump it out, and then you treat it and then again recycle the reactive agents. That's a lot of effort. But instead of that, you can put these electrodes and then you can control those, the migration and pumping efforts. What we did is, we try to exploit this. This can be applied in clay type soils also, but you have to augment with electrokinetics. If you don't use the electrokinetics, you cannot really flush anything through the clay. So what we try to do is we try to use the chemical oxidation or chemical reduction. Again, this is the chemistry part. With that one, you can degrade the organics. You don't have to. You will not get anything into the electrodes to pump it out. You in situ degradation of the contaminants. So there is a chemical degradation and biological degradation. Bioremediation is biologically degrading. That might be taking a long time. So instead of that, if I use the chemical oxidant, then if you have a right chemistry, the chemicals get degraded into non-toxic form. So that's one of the things is this H2O2. So hydrogen peroxide, if you inject it, and in water treatment, they inject H2O2 and they inject iron source. And people don't believe that, you don't need to inject iron into the soil because you have a soluble iron in any soil that you deal with. So we demonstrated that one. So you just put it in H2O2 in the soil, in the electrode compartment, have it flush through the soil, and you get the degradation of the phenanthrene. It's one of the nasty and non-volatile, not easily degradable contaminant, PAH, and that can be removed by that. And if you have a metal simultaneously, those can be transported to the electrodes. We also did some testing with the nano iron particles. It's kind of opposite to oxidant. Nano iron is the reducing it. If you use that one, again, some contaminants get reduced easily than oxidizing. So we did that kind of information also. So again, it's a combining chemical reduction with the electrokinetics. So this kind of technology has been, proved in Europe in some cases. Here is the soil. You see, look at the, how it is done in the field. This cannot be done on a large area. If you have a small area where you have a contamination has occurred, it's called source zone remediation. You will have a series of wells, and some of them are designated as anodes, some of them are designated as cathodes, and so you see this one. So this is another site where they applied. So there are some case studies. This is the lasagna process, they call it. So they put in electrodes, and here is the contamination, groundwater contamination, the soil contamination, showing the contours of the contamination levels. And then after treatment, the contaminations have decreased significantly. See, ultimately, the concentrations are totally gone. There is other way to do it. You can put a E barrier or kind of electrokinetic barrier that the water, contaminated water, go through that one, and then you have oxidation reduction reactions happen in that E barrier or electrokinetic barrier, and then you will see the contamination degrade. So people have done experiments with in the lab, looking at these kind of scenarios. So people have did all this stuff. So any questions on this one? I just want to make sure that I don't take too much time. I think I have been talking for a long time. See if anyone has any questions on what I covered.
So someone asked in the chat box, like, what would be the possible uses of phytoremediation, biomass, biochar? Few questions are there. And
yeah. So the one question, that's not related to what I was talking about is like a different question that we will discuss later on. Phytoremediation, biomass. So you really need to look at it, what you have in what contamination have taken by the plants. Are you talking about the metals or any kind of a residual? You're talking about any residual organics. So depending upon that it varies. And then if you want to use that, any biomass can be used for producing the biochar. But then, what happens to those contaminants, right? So if those contaminants are in the biochar, and do you want to use the biochar that has a lot of toxic metals in them? So first thing that you have to do, when you are using the biochar, no matter what source you get it from, you need to look at the leachability of that biochar and see if there are any issues associated with any kind of a contaminants in the biochar. We did that kind of testing. So whenever we got the biochar from commercial vendors, and some biochars had a lot of pHs and metals. So obviously you don't want to use that kind of biochar, indiscriminately. So you need to characterize the biochar. I mean, I don't know, what kind of contaminations you will have plants, and how they get affected by your production process of biochar, and so that needs to be accounted, right? So can you address on limitations of electrokinetics? So yeah, I'm just going to go to that one. Any studies on arrangement of cathodes? Yeah, typical, they're there, and you can do the modeling to come up with optimal spacing. So yeah, you can use the electrokinetics in stabilization. Basically, let's say you want, what is the stabilizing agent that you want to use? And if it is some form, let's say you're using polymer, and if you want to do the in situ stabilization, so you can try to inject that polymer solution electroosmotically through the soil. So the electrokinetics can be used as a delivery system for stabilization if you are interested in. what kind of solvents to use. So yeah, we tried a lot of different types of solvents, co-solvents, and surfactants. I can send you the papers on that one. We tried multiple types of co-solvents, some of them are effective, some of them are not effective. So you need to look at those things. Any other questions? Let me see if I missed something. So what is standard document for our solvents? There's no standard, but like you really do some treatability studies and select the solvent that you want, and make sure that solvent that you use, especially if it happens to be the in situ remediation process, you're going to leave some residual amount in the soil, so it should not have any effects. So you're trying to take the contamination, but in the process you might have introduced unwanted contamination. You may be looking at one thing, but so you cannot really recover everything that you inject into the soil. You know what I'm saying? Let's say I'm trying to use this polymer or surfactant or solvent. Let's say I'm using the solvent. The chemistry is good, but like not everything is recoverable. Whatever you have injected solvent, right? So if some solvent is still remaining in the soil, and if that is posing a lot of environmental issues, you're causing the newer problem than the existing problem. You're solving the existing problem, but you're creating a new problem. That's why in the US you have to take the permission from the regulating agency to inject. So they don't allow injecting anything you want. They are very careful. So you need to be you need to demonstrate, even if some residual amount is remaining, that's not going to cause any problems. So those issues have to be taken into account. Let's see, any other questions? Let's see. Yeah, what is the best strategy to remediate large acres of land, taking cost factor into account? So that's why I'm saying you need to have I highly suggest, let's say you're working on any research on a particular technology, but you need to have a different, you need to understand what are the different technologies are and what their applicability is. Because if you're working in industry, if you are ignorant about all the technologies, somebody out there, the technology providers, whatever technology they have, they will say that it works for every situation that you have. That's very important to know what the limitations of technologies are. For the large acres of land, obviously, depending upon the contamination, if it is, the contamination is close to shallow depth, then phytoremediation is the one that we use. If it is a large area and contamination is deeper, you generally use the vertical barriers and you don't try to remove the contamination. You rather contain it rather than remediating it. So you really have to find out which is the best option that you're looking at it. So when you're doing the research, it's fascinating. I generally don't present a lot of technical details. I can go into, we did the geochemical modeling and other things, but my basic message is understand the fundamental geochemistry, and then you can engineer it. Let's say if pH is responsible for this one, then I will try to, alter the pH to favor whatever we want. So my term is engineer the geochemistry. If you are using the bio and phyto, engineer the biogeochemistry. So you understand the biogeochemistry and you identify what are the things that are limiting your remediation, and then then come up with a approach to overcoming those limitations. And then how do you implement that one? So that's called, that's what I'm trying to say, engineering it. Any questions? Any other questions that you have?
But
Thank you
also,
so much, sir. Thank you so much.
Yeah.
Yes, sir.
Yeah.
I think all comments and queries are done. Is there anyone who need to ask anything, and is there anything is left? Is it fine all?
Yeah, just let's see if you have any
Yeah, I
questions. If you don't have any questions, then just let me give them a couple of more minutes.
Yes, sir. So there is, can you please say something about your lab facilities and the instruments?
I'll show you a video of my lab in one of the future lectures. Yeah, our lab has all the equipment that can be used to do the material characterization. And so all the standard soil testing that can be done on any waste materials. We fabricate small scale and large scale test setups depending upon our needs. And we have all the equipment that is needed to do the chemical analysis or preparing the samples. So we, obviously have mixers, shakers, GCs, the UV, we have AA, and we use our central facility for SCM, XRD, and we do the biological testing. We collect the samples to be able to preserve the microbes, and then sometimes we do the DNA extraction. We have a DNA facility that can analyze the microbes for us. So and I mean, we develop the lab as needed basis. I mean, sometimes you have a research project that needs something specially for that. Unlike, in many places in the US, we get only one project funded on particular topic. So let's say I got funding on electrokinetics, and that's it. I need to do as much as I can on that topic, whatever I proposed, and then move on to the next topic, because I will not be able to get additional funding on even if I have done good research, because a lot of times the funding agencies say that, okay, we give you initial funding to develop the technology or to understand the fundamentals, and then you need to generate the sustainable funding mechanism through the industry or other applications. So that's why you see I keep on moving on to different topics, because that's the only way that we can sustain our lab research or field research, our research in general. But good thing is, we do some initial work, and other people's take on that idea and do a lot of detailed studies. I have no problem if somebody takes our idea and expands it in different directions. So there are a lot of papers on electrokinetics. If you go to my website, you will be able to find many. So one of the fascinating things with electrokinetics, when you do the research, you try to come up with a solution, right? So when we were doing the electrokinetic research, every time we do the research, we find new issues to resolve. And so it's not like solving the problem. We identify some new issues and new ways of addressing those issues. So one after the others, we had to conduct so many different studies to get a good grip on the topic. Whereas some other projects, within one project, we will come up with a solution that could be used by practitioners. But that does not happen in many situations. So especially electrokinetics is so complicated, and And you don't want to give up because it has so many different advantages. It can work on any different type of soil, any type of contamination, even mixed contamination. You can do in situ, ex situ. So it has so many advantages that in some cases you don't have any alternative technology other than using this. So in terms of the cost, it could be expensive. It could be time consuming if there is no other competing technology for that. That cost may be acceptable. How many of you are working on remediation research, soil or groundwater research? And if you can put just topic that you're working on in the chat box, just what is the technology that you're working on, like a phytoremediation, bioremediation, something, any technology anybody is working on this, any. If you are not working on these kind of topics, I think that's even the reason why you need to start initiating research on this topic. And of course, you need some lab facilities to do research. But as I said, the best way is to initially collaborate with your environmental engineering faculty who work only on water related projects, but their equipment then can be utilized.
So a few responded like they work on the soil stabilization and remediation, phytoremediation in mines overburden and like that.
Very good, very good. Yeah, can you keep typing this so that I can understand what kind of work is going on right now? Yeah, any work that you're doing related to soil remediation or groundwater remediation or assessment?
Phytorestoration of mining soil and GIS and groundwater pollution, not the treatment. That is something new. And geotechnical characterization of leachate affected soil. Yes, sir, these are there.
Very good. So I think, what I wanted to do is to, I don't talk about so many technical details in my typical presentations, but I wanted to cover more technical aspects. So in tomorrow's lecture, I will talk about another technology with more technical aspects.
Sure, sir. So shall we end the session today?
Yeah, sure. I'm open for that. So it's a 1 minute past our scheduled time. So
yes,
it would be
sir.
And they need time to digest what I covered today. So tomorrow you can ask me questions on, if you come up with any additional questions, you can ask me tomorrow. Okay, sounds good.
Yeah.
You want to wrap it up, Meghna?
Yes, sir. Yes, sir. So thank you so much, sir, for enlightening us. And thanks to all for attending. And we'll meet at 4:30 p.m. tomorrow sharp. And if there is any update or anything, we'll update you in the group, which we have prepared. So whoever is not joined the group, WhatsApp group, they can also join, okay, for more updates and all. Thank you so much. Okay, good night, guys. Good night, sir.
Good night.
Okay, sir.
Okay, I'm going to leave now.